Welcome back. Tonight, we settle in with the patient astronomers of the early 19th century, who spent their nights squinting through brass telescopes, charting the dark spaces between Mars and Jupiter, where they suspected, correctly, as it turned out, that something had gone missing, and who, one by one, began to find the scattered remnants of that celestial puzzle, tiny points of light drifting slowly against the fixed stars, each discovery adding another name to the growing catalogue of minor planets. Before we begin, take a moment to like the video and subscribe, but only if these stories help you drift off peacefully. Now, dim the lights. Pull the blanket a little closer. And together, let us ease gently into tonight's story. In the quiet years of the 18th century, when candlelight still flickered in the observatories of Europe and astronomers kept their vigils beneath the turning heavens, there emerged a curious mathematical observation that would occupy the minds of natural philosophers for decades to come. This observation concerned the spacing of the planets, those wandering lights that had fascinated humanity since the earliest days of skyward contemplation, and it suggested that the arrangement of our solar system followed a pattern so elegant, so orderly, that it seemed to whisper of some deeper cosmic design. The story begins with a German schoolteacher and astronomer named Johann Daniel Titius, who in the year 1766 noticed something rather remarkable about the distances between the Sun and its attendant worlds, a pattern that had perhaps been waiting quietly to be discovered, like a melody hidden within what had seemed mere noise. Titius was translating a work of natural philosophy by the Swiss author Charles Bonnet when he found himself moved to insert a small footnote of his own, a passage that he tucked modestly into the larger text, as though uncertain whether his observation warranted much attention at all. In this footnote, Titius described a simple numerical sequence that appeared to correspond, with surprising accuracy, to the distances of the known planets from the Sun. The sequence itself was not complicated, and indeed its simplicity was part of what made it so compelling to those who believed that the universe operated according to elegant mathematical principles. One begins with the number 0, then 3, then 6, and thereafter each subsequent number is simply double the one that came before it, so that the sequence proceeds as 0, 3, 6, 12, 24, 48, 96, and onward into ever larger values. To apply this sequence to planetary distances, one adds 4 to each number and then divides by 10, which yields a series of values expressed in astronomical units, that convenient measure where 1 unit equals the distance from the Earth to the Sun. When Titius performed these calculations, he found that the results corresponded remarkably well to the actual positions of the planets as they were then known. Mercury, the innermost world, sits at approximately 4/10 of an astronomical unit, and the formula gives precisely 4/10. Venus orbits at roughly 7/10 of a unit, and the formula predicts 7/10. Earth, by definition, circles at 1 unit from the Sun, and the formula yields 10/10, which is to say 1 unit exactly. Mars, that reddish wanderer, occupies an orbit at approximately 1 1/2 astronomical units, and the formula gives 16/10, or 1 6/10 units, which is close enough to suggest that something meaningful might be occurring. But here the sequence presented a puzzle, for when Titius continued his calculations, the next value in the series pointed to a distance of 28/10 of an astronomical unit, or 2 8/10 units from the Sun, and at this location there was no planet to be found. The space between Mars and Jupiter, which the formula indicated should contain a world, appeared to be empty, a gap in what otherwise seemed a harmonious arrangement. Beyond this mysterious vacancy, Jupiter did indeed orbit at approximately 5 2/10 units, reasonably close to the predicted 5 2/10, and Saturn, the most distant planet then known, circled at roughly 10 units, which accorded well with the formula's prediction of 10 units. The pattern held everywhere except at that one troublesome distance, that region of space at 2 8/10 astronomical units where mathematics suggested a planet should exist, but where telescopes revealed nothing but the black stillness between worlds. Titius himself did not make a great fuss about his observation, and his footnote might well have been forgotten had it not caught the attention of a more prominent astronomer named Johann Elert Bode. Bode was the director of the Berlin Observatory and a man of considerable influence in the astronomical community of his day, and when he encountered the planetary spacing rule in 1772, he recognized its potential significance and began to champion it widely. It was Bode who brought the formula to the attention of the broader scientific world, publishing it in his own astronomical writings and discussing it in his correspondence with other natural philosophers across Europe. Through his efforts, the relationship became known as the Titius-Bode law, though some would simply call it Bode's law, a name that persists in astronomical literature to this day, carrying with it perhaps a slight injustice to the modest schoolteacher who first noticed the pattern. Bode was not merely interested in the mathematical elegance of the sequence, but was deeply curious about the apparent gap it revealed. He speculated openly about the possibility that a planet might indeed exist at the predicted distance, a world that had somehow escaped detection, perhaps because it was small or faint or moved in such a way as to have eluded the casual sweeps of telescopic observers. This was not mere whimsy on Bode's part, for he lived in an age that took very seriously the notion that the cosmos was constructed according to rational and harmonious principles. The Enlightenment had brought with it a confidence that the universe was comprehensible, that its workings could be understood through careful observation and mathematical reasoning, and that the patterns one discovered in nature were evidence of an underlying order that reflected, many believed, the wisdom of a divine creator. This philosophical context is important for understanding why so many astronomers of the period were willing to invest considerable time and energy in searching for a planet that might not exist. The idea that the solar system should contain gaps, that the distances between planets should follow no particular pattern, seemed to many thinkers deeply unsatisfying, even aesthetically offensive in an age that prized symmetry and proportion. If the other planetary distances conformed so neatly to a simple mathematical rule, then surely the exception at 2 8/10 astronomical units must be just that, an exception, a temporary embarrassment that would be corrected once the missing planet was located. The universe, they felt, would not be so untidy as to leave an empty space where a world ought to be. It is worth noting that the idea of a missing planet between Mars and Jupiter was not entirely new with Titius and Bode, for the great Johannes Kepler himself had entertained similar thoughts more than a century and a half earlier. Kepler, whose 3 laws of planetary motion remain fundamental to our understanding of orbital mechanics, had been struck by the unusually large space separating Mars from Jupiter and had speculated that an undiscovered planet might occupy this region. In his work Mysterium Cosmographicum, published in 1596, Kepler attempted to explain the spacing of the planets through a model involving nested geometric solids, the so-called Platonic solids, and though this model ultimately proved incorrect, it reflected the same deep conviction that planetary distances must follow some intelligible pattern. Kepler wrote that between Mars and Jupiter he had placed a new planet, and though he did not pursue this speculation with the same vigor that later astronomers would, His words planted a seed that would germinate across the generations. The confidence in the Titius-Bode law received a tremendous boost in the year 1781, when an event occurred that seemed almost too perfect to be coincidence. William Herschel, a German-born musician who had become an astronomer of remarkable skill and dedication, was conducting a systematic survey of the heavens from his home in Bath, England, when he noticed a peculiar object that did not behave like a star. Upon closer observation and consultation with other astronomers, it became clear that Herschel had discovered a new planet, the first to be found since antiquity, a world that would eventually be named Uranus after the ancient Greek deity of the sky. This discovery alone would have been momentous, but what made it particularly significant for believers in the Titius-Bode law was the distance at which Uranus orbited the Sun. When astronomers calculated the orbit of this new planet, they found that Uranus circled the Sun at approximately 19 2/10 astronomical units, a distance that corresponded remarkably well to the next value in the Titius-Bode sequence, which predicted a planet at 19 6/10 units. The agreement was not perfect, but it was close enough to convince many astronomers that the law must represent something real about the structure of the solar system, some fundamental principle governing the spacing of worlds. If the law had successfully predicted the position of a planet that no one had known existed, a planet discovered entirely independently of any search motivated by the law itself, then surely the gap at 2 8/10 units must also contain a planet waiting to be found. The discovery of Uranus transformed the Titius-Bode law from an interesting curiosity into what seemed like a vindicated prediction, and the hunt for the missing planet began in earnest. Among those most determined to fill the gap was Baron Franz Xaver von Zach, a Hungarian astronomer who had built a distinguished career and would eventually become the director of the Seeberg Observatory near Gotha in Germany. Von Zach was a meticulous man, organized and thorough in his approach to astronomical problems, and he found the apparent vacancy between Mars and Jupiter to be a personal affront to his sense of cosmic order. Beginning in 1787, he undertook a careful study of the region of sky where the hypothetical planet should appear, calculating where along the zodiac it might be found based on the Titius-Bode prediction and the orbital mechanics that would govern a body at that distance from the Sun. Von Zach's calculations suggested that the missing planet, if it existed, would complete one orbit around the Sun in approximately 4.5 years and would move against the background stars at a rate that should be detectable with patient observation. He devoted countless nights to scanning the relevant portions of the sky, hoping to spot a slowly moving point of light that would betray itself as something other than a fixed star. The work was painstaking, for the region in question contained thousands of faint stars, any one of which might be the sought-after planet on any given night, and only careful comparison of observations taken on different occasions could reveal which objects were moving and which were stationary. As the years passed and no planet revealed itself, von Zach grew increasingly frustrated, though his determination did not waver. He began to suspect that the planet might be smaller than expected, fainter and more difficult to detect than the known worlds, and this suspicion would eventually prove remarkably prescient. He also recognized that a single observer, no matter how dedicated, might simply miss the planet by chance, observing the wrong part of the sky on the wrong night or failing to notice a moving object among the multitude of background stars. What was needed, he concluded, was a coordinated effort involving multiple observers stationed across Europe, each responsible for searching a particular section of the zodiac, so that the entire region could be surveyed systematically and thoroughly. This idea would eventually lead von Zach to organize a collaborative search involving 24 astronomers, each assigned a specific zone of the sky to monitor, a project that represented one of the earliest examples of large-scale international scientific cooperation. But that effort, and the discoveries it would inspire, belong to a later portion of our story, to the early years of the 19th century when the gap would at last begin to yield its secrets. For now, it is enough to note that as the 18th century drew to a close, the astronomical community had convinced itself, through a combination of mathematical reasoning, philosophical conviction, and the encouraging example of Uranus, that a planet must exist at the predicted distance, and that its discovery was merely a matter of time and diligent observation. The belief in cosmic harmony that motivated this search was not naive or irrational, though from our present vantage it might seem overly optimistic. The astronomers of the Enlightenment had witnessed extraordinary successes in the application of mathematical methods to natural phenomena, from the precise prediction of cometary returns to the explanation of planetary perturbations through gravitational theory. They had every reason to believe that the universe operated according to comprehensible laws and that apparent irregularities were simply invitations to deeper investigation. The gap between Mars and Jupiter was, in this view, not a flaw in the cosmic design but a challenge to human ingenuity, a puzzle posed by nature that the patient observer would eventually solve. And so they searched, night after night, year after year, confident that the missing planet was out there, circling quietly in the darkness at 2 8/10 astronomical units from the Sun, waiting to complete the harmony of the spheres. In the autumn of the year 1800, as the leaves began to turn across the German countryside, and the nights grew longer and more conducive to astronomical observation, a small gathering of gentlemen astronomers made their way to the village of Lilienthal, which lies not far from the city of Bremen in what was then the electorate of Hanover. They came at the invitation of Johann Hieronymus Schroeder, a man who had once served as a magistrate and chief administrative officer of the district, but who had devoted much of his considerable personal fortune and nearly all of his intellectual energy to the construction and maintenance of what had become one of the finest private observatories in all of Europe. The meeting took place in September, when the summer heat had subsided and the atmosphere had begun to settle into that particular clarity which autumn sometimes brings to northern latitudes, and the purpose of this gathering was nothing less than the systematic organization of a search for a planet that no one had yet seen, but which many astronomers of the era believed must surely exist. The driving force behind this meeting was Franz Xaver von Zach, a Hungarian-born astronomer who had risen to prominence in the astronomical circles of Central Europe and who served as the director of the Seeberg Observatory near Gotha, working under the patronage of Duke Ernst II of Saxe-Gotha-Altenburg. Von Zach was a man of tremendous organizational ability and wide correspondence, maintaining regular communication with astronomers across the continent and beyond, and he had become increasingly convinced that the apparent gap in the solar system between the orbits of Mars and Jupiter, a gap that had troubled mathematical astronomers for some decades, must contain an undiscovered planetary body. This conviction was rooted in a numerical curiosity that had been popularized by Johann Daniel Titius and later by Johann Elert Bode, a simple mathematical progression that seemed to predict the distances of the known planets from the Sun with remarkable accuracy, and which also predicted that a planet should exist at a distance corresponding to the space between Mars and Jupiter. The discovery of Uranus by William Herschel in 1781 had lent considerable credibility to this numerical pattern, as Uranus appeared at very nearly the distance the progression had predicted, and this success had emboldened those who believed that the missing planet at the Mars-Jupiter gap was waiting to be found. Schroeder's observatory at Lilienthal was an ideal location for such a meeting, for it represented one of the most ambitious private astronomical enterprises of the age. Johann Schroeder had begun constructing his observatory in 1781, the very year of the discovery of Uranus, and over the following 2 decades he had assembled a remarkable collection of instruments and telescopes. The crown jewel of his establishment was a magnificent reflecting telescope with a focal length of 27 feet, a substantial instrument that required considerable effort to operate, but which provided views of the heavens that few other observatories in Europe could match. Schroeder had commissioned this telescope from Johann Gottlieb Friedrich Schrader, a skilled instrument maker, and the observatory grounds also contained several smaller telescopes, a transit instrument for precise positional measurements, and various other apparatus necessary for serious astronomical work. The buildings themselves were designed with the particular requirements of astronomical observation in mind, and the surrounding landscape was relatively flat and free from obstructions that might interfere with observations near the horizon. It was here, in this comfortable and well-equipped setting, that the astronomers gathered in September of 1800 to discuss their plans for the systematic search. The society that emerged from this meeting was given the formal name Vereinigte Astronomische Gesellschaft, which translates into English as the United Astronomical Society, though it quickly acquired a rather more colorful nickname that has persisted in the historical literature. The members themselves, or perhaps their contemporaries, began to refer to the organization as the Himmelspolizei, a German term meaning the celestial police, and this name captured something of the methodical, patrol-like nature of the work they intended to undertake. The English rendering, the celestial police, conveys the same sense of vigilant watchfulness, of systematic surveillance of the heavens in search of an interloper moving among the fixed stars. There is something rather charming about this nickname, suggesting as it does a kind of cosmic constabulary keeping watch over their assigned territories, alert for any suspicious movement among the unchanging stellar population. The plan that von Zach proposed was elegant in its simplicity and thoroughly Germanic in its systematic thoroughness. The zodiac, that band of sky through which the sun, moon, and planets appear to move, extends roughly 8 degrees on either side of the ecliptic and contains the 12 familiar constellations of astrological tradition. Any planet moving in an orbit between Mars and Jupiter would necessarily be found somewhere within this zodiacal band, for the planets all orbit in roughly the same plane, and so it made sense to concentrate the search efforts on this region rather than attempting to survey the entire celestial sphere. Von Zach divided the zodiac into 24 zones, each spanning 15 degrees of celestial longitude, and he proposed that each participating astronomer should take responsibility for the careful and repeated observation of one of these zones. By distributing the work in this manner, the entire zodiac could be kept under continuous surveillance, and any planet moving slowly through this region would eventually be detected as it crossed from one zone into another. The membership of this society included many of the most distinguished astronomers of German-speaking Europe, along with several notable figures from neighboring countries. Johann Schroeder himself was naturally a central figure, serving as the president of the society and providing the facilities for its initial meeting. Franz Xaver von Zach served as the secretary, a role that suited his talents for organization and correspondence, and he took it upon himself to coordinate the efforts of the various members and to collate their observations. Heinrich Wilhelm Matthias Olbers, a physician from Bremen who practiced medicine during the day and observed the heavens at night, was among the most active and capable members of the group, possessing both considerable skill as an observer and a deep understanding of orbital mechanics. Carl Ludwig Harding, who served as an inspector at Schroeder's observatory and assisted with much of the practical work there, was another key participant, a careful and patient observer who would later make significant contributions to the early discoveries of this period. Among the other members were Ferdinand Adolf von End, a nobleman and amateur astronomer from the region around Ceres, whose wealth and social position gave him the leisure to pursue astronomical studies, and Johann Gildemeister, a merchant from Bremen whose commercial success had allowed him to indulge his interest in the sciences. The society also included or extended invitations to astronomers in other countries, for von Zach's correspondence network was extensive, and he recognized that a truly systematic search would benefit from the participation of observers at different longitudes and in different climatic conditions. Letters were sent to astronomers across Europe, inviting them to join the effort and assigning them their designated zones of the zodiac to patrol. The response was generally enthusiastic, for the idea of discovering a new planet held considerable appeal, and the prospect of participating in a coordinated international scientific endeavor was attractive to many who felt isolated in their observatories. The methodology that the celestial police intended to employ was straightforward in principle but demanding in practice. Each observer was to prepare detailed charts of all the stars visible in their assigned zone, marking the position of each star with care and precision. These charts would then serve as reference documents, and by comparing the appearance of the sky on successive nights with the recorded positions on the charts, any object that had moved would become apparent. A planet, even one moving slowly across the background of fixed stars, would eventually betray itself by appearing in a slightly different position relative to the stars around it, and repeated observations over several nights would confirm the reality of this motion and distinguish a genuine planetary body from a mere error of observation or recording. This method required considerable patience and meticulous attention to detail, for the stars in any given region of the zodiac number in the hundreds or thousands when one includes those visible through a telescope, and the motion of a distant planet might amount to only a small fraction of a degree per day. The work was well suited to the temperaments of the astronomers involved, many of whom were precisely the sort of careful, methodical individuals who found satisfaction in the gradual accumulation of accurate data. There was nothing glamorous about the task, nothing that would produce immediate results or dramatic discoveries, but there was a quiet satisfaction in the systematic coverage of the sky, in the knowledge that one's assigned zone was being watched and that any planetary intruder would not escape notice. The observers met periodically to discuss their progress, to compare notes, and to ensure that their methods were consistent and their charts compatible. Von Zach maintained regular correspondence with all the members, encouraging them in their work and keeping them informed of developments at other observatories. And yet, for all the careful planning and systematic organization, for all the learned discussions at Lilienthal and the diligent patrol of the zodiacal zones, the celestial police were destined to be surprised by events. The discovery they sought, the first detection of the missing planet between Mars and Jupiter, would come not from one of their own members, not from one of the assigned zones being carefully watched by their designated observer, but from an astronomer working in Sicily who had not even received his invitation to join the society when he made his observation. Giuseppe Piazzi, the director of the Palermo Observatory in the Kingdom of the Two Sicilies, was engaged in the altogether different task of compiling a star catalogue when, on the first night of the new century, he noticed a small point of light that seemed out of place. Piazzi was not searching for a planet, had no knowledge of the celestial police or their systematic search, and indeed the letter inviting him to join the society was still making its way southward through the postal routes of Europe when he made his discovery. There is something gently ironic about this circumstance, something that speaks to the unpredictable nature of scientific discovery despite the best efforts at organization and planning. The celestial police had divided the heavens among themselves with Prussian efficiency, had established protocols and methodologies, had recruited some of the finest observational astronomers in Europe to their cause, and yet the quarry they sought was first sighted by someone who was not part of their hunt at all. Piazzi was simply doing his regular work, observing stars and recording their positions for his catalogue, when he happened upon the object that would come to be called Ceres. The discovery was, in a sense, accidental, though it must be said that Piazzi's own skill and diligence in recognizing that something unusual had appeared in his field of view was essential to the achievement. A less careful observer might have dismissed the point of light as an ordinary star and moved on to the next entry in his catalogue. The members of the Celestial Police did not receive news of Piazzi's discovery for some months, owing to the slowness of communication in that era, and to Piazzi's own initial uncertainty about what he had found. By the time the astronomical community became fully aware that something significant had been observed in Palermo, the object had moved too close to the sun in the sky to be observed, and there followed an anxious period during which mathematicians attempted to calculate where the object might reappear. But that is a matter for another portion of our story. And for now we may simply note that the Celestial Police, having been anticipated in the discovery of the first object, would go on to play important roles in the discoveries that followed. The Society continued its work, its members remained in communication, and the systematic approach that von Zach had championed would prove valuable in the years ahead as more objects were found in the region between Mars and Jupiter. The Lilienthal Observatory itself, that gracious establishment where the Society had been founded, would not survive the turbulent years that followed. The wars that swept across Europe in the wake of the French Revolution and the rise of Napoleon brought destruction to many places, and in 1813 French troops passing through the region set fire to Schroeder's observatory, destroying most of his instruments and much of his recorded observations. It was a considerable loss to astronomy, and Johann Schroeder, by then an elderly man, never fully recovered from the blow. He died 3 years later, in 1816, having devoted the greater part of his life to the patient study of the heavens. But the society he had helped to found, and the systematic approach to planetary searching that it represented, had already achieved results that would long outlive the buildings in which its members had first gathered on those September evenings in 1800, when the work of patrolling the zodiac had seemed so promising and the missing planet had seemed so tantalizingly close to discovery. On the first night of a new century, in a quiet observatory perched above the rooftops of Palermo, a Theatine monk turned his telescope toward the heavens and unknowingly changed the map of our solar system forever. The date was January the 1st, 1801, and Giuseppe Piazzi, a man of patience and methodical precision, was engaged in work that he considered rather ordinary, the careful compilation of a star catalogue that would occupy him for many years. He could not have known, as he settled into the familiar rhythms of his nightly observations, that this particular evening would mark the beginning of what we now call the golden age of asteroid discovery, a period of quiet wonder and gradual revelation that would reshape humanity's understanding of the space between Mars and Jupiter. Giuseppe Piazzi had arrived at his vocation through a somewhat winding path, as many astronomers of his era did. Born in 1746 in the town of Ponte in Valtellina, then part of the Cisalpine Republic, he entered the Theatine order as a young man, drawn to the contemplative life and the intellectual pursuits that religious orders often fostered in that age. The Theatines placed considerable emphasis on education and scholarship, and Piazzi found himself teaching mathematics and philosophy at various institutions throughout Italy, his mind naturally inclined toward the precise and the measurable. In 1780, he was appointed to the chair of mathematics at the Academy of Palermo in Sicily, and it was there, beneath the warm Mediterranean skies, that he began to cultivate what would become his life's great work, the establishment of a proper astronomical observatory and the creation of a comprehensive catalogue of the fixed stars. The observatory at Palermo was modest by the standards of the great European institutions, but Piazzi had equipped it with care, travelling to Paris and London in the late 1780s to acquire the finest instruments he could obtain. Chief among these was a magnificent 5-foot vertical circle constructed by the renowned English instrument maker Jessie Ramsden, a device of exceptional precision that allowed Piazzi to measure the positions of stars with remarkable accuracy. The Ramsden circle was a thing of beauty in its own right, a testament to the craftsmanship of the age, with its finely graduated scales and delicate crosshairs that enabled an observer to fix the location of a celestial object against the slowly wheeling dome of the heavens. Piazzi treasured this instrument deeply, understanding that the quality of his star catalogue would depend entirely upon the reliability of his measurements, and he had become quite skilled in its use over the years that followed his return to Sicily. The work of compiling a star catalogue is perhaps not the most glamorous pursuit in astronomy, but it is among the most valuable, for accurate knowledge of stellar positions forms the foundation upon which all other celestial observations must rest. Piazzi approached this task with the diligence and patience that characterized his monastic training, spending night after night at the eyepiece of his telescope, recording the positions of thousands of stars with painstaking care. On that first night of the new century, he was engaged in precisely this sort of routine work, observing a region of the sky in the constellation Taurus, the Bull, where the winter stars shine with particular clarity in the northern hemisphere. The air above Palermo was steady that evening, as it often was in the Sicilian winter, and Piazzi could see the stars as sharp points of light through the lens of his instrument. Among the many stars he observed and recorded that night was one of approximately the 8th magnitude, which is to say a star too faint to be seen with the unaided eye but easily visible through even a modest telescope. There was nothing remarkable about this object at first glance, nothing to distinguish it from the countless other dim stars that populated his field of view. Piazzi noted its position carefully, as he did for all the stars he observed, writing down the coordinates in his observing log with the neat hand of a practiced astronomer. The night passed quietly, the hours marked by the slow drift of the constellations across the meridian, and eventually Piazzi closed up the observatory and retired to his quarters, satisfied with another productive evening of work. The following night, January the 2nd, Piazzi returned to the same region of sky to continue his observations, as was his custom, for he often observed the same stars on multiple nights to verify the accuracy of his measurements and to catch any errors that might have crept into his work. It was then that he noticed something peculiar about the faint star he had recorded the previous evening. Its position had shifted ever so slightly, moving a small but unmistakable distance against the background of the fixed stars. This was most unusual, for the fixed stars, as their name implies, do not move relative to one another in any way that can be detected over the course of a single night or even a single year, their apparent positions changing only through the slow effects of precession over centuries and millennia. An object that moved visibly from one night to the next was something else entirely, something that belonged not to the distant sphere of the stars but to our own solar system, wandering among the fixed points of light as the planets do. Piazzi's first assumption, and it was a reasonable one given the knowledge of his time, was that he had discovered a comet. Comets were known to appear unexpectedly and to move across the sky in just this fashion, their fuzzy heads and streaming tails becoming visible as they approached the sun on their long elliptical orbits. Many astronomers of the era kept a hopeful eye out for new comets, for such discoveries brought considerable prestige, and Piazzi might well have felt a flutter of excitement at the thought that his patient cataloguing work had yielded such an unexpected prize. Yet as he continued to observe the object over the following nights, something about it troubled him, for it showed none of the characteristics that typically marked a comet. Through his telescope, it appeared as a sharp point of light, entirely stellar in appearance, with no trace of the nebulous haze or elongated tail that would indicate a cometary nature. Night after night through the early weeks of January, Piazzi returned to his observatory to track the mysterious object, recording its changing position with the same methodical care he applied to his star catalogue work. The object continued to move, tracing a slow path against the background stars, and Piazzi began to entertain a remarkable possibility, one that aligned with theoretical predictions that had circulated among astronomers for some years. There existed, in the mathematical musings of certain natural philosophers, a suggestion that there ought to be a planet orbiting the Sun in the vast gap between Mars and Jupiter, a gap that seemed unnaturally large when one considered the regular spacing of the other known planets. The so-called Titius-Bode law, a numerical curiosity that appeared to predict the distances of the planets from the Sun with surprising accuracy, indicated that a planet should exist at approximately 2.8 astronomical units from the Sun, precisely where the gap lay empty. Could this unassuming point of light, this supposed star that refused to stay fixed in its place, be that long-sought missing planet? Piazzi observed the object a total of 24 times over the course of 41 nights, gathering a precious set of positional data that would prove invaluable in the months to come. His observations were necessarily sporadic, interrupted by cloudy weather and by the ordinary demands of life, but he persisted with quiet determination, aware that he might be witnessing something of genuine significance. As January drew toward its close, however, Piazzi fell ill, his body weakened perhaps by the long cold nights spent at the telescope, and he was forced to suspend his observations for a time. When he recovered sufficiently to return to his work, he found that the object had moved ever closer to the Sun in the sky, lost in the bright twilight glow that precedes sunrise, and by the 11th of February it had become entirely unobservable, swallowed by the solar glare as it continued along its orbital path. There remained the question of what to do with his discovery, and here Piazzi displayed a certain hesitancy that was perhaps characteristic of his cautious nature. He had observed the object for less than 6 weeks, a span of time that was insufficient to determine its orbit with any confidence, and he was not entirely certain what manner of celestial body he had found. To announce a new planet prematurely, only to have it revealed as an ordinary comet, would be an embarrassment that he was reluctant to risk. Yet he also understood that other astronomers would need to search for the object when it emerged from the solar glare later in the year, and for that they would require his observational data. On January the 24th, while his observations were still ongoing, Piazzi wrote letters to 2 of the most prominent astronomers in Europe, Johann Alert Bode in Berlin and Jerome Lalande in Paris, informing them of his discovery and sharing some of his positional measurements. In his letters, Piazzi was somewhat guarded about the nature of the object, referring to it initially as a comet while hinting that it might be something more interesting. The mails of the era traveled slowly, carried by horse and ship across the mountains and seas of Europe, and some weeks would pass before his correspondents received word of the discovery. Piazzi also communicated with his colleague Bannabar Oriani in Milan, with whom he had a long friendship, and it was to Oriani that he expressed most openly his suspicion that this was no ordinary comet but a new member of the planetary family. The delay in announcing his discovery has sometimes been characterized as excessive caution or even a desire to secure priority, but it seems more likely that Piazzi simply wished to gather more data before committing himself to a definitive claim, a scruple that speaks well of his scientific integrity, even if it caused some frustration among his colleagues. When the time came to give his discovery a name, Piazzi chose to honor both the ancient and the contemporary, the divine and the earthly. He called the object Ceres Ferdinandia, a double name that paid tribute to the Roman goddess of grain and harvest, Ceres, who was particularly associated with Sicily, the breadbasket of the ancient Mediterranean world, and to King Ferdinand IV of Sicily, the Bourbon monarch under whose patronage Piazzi's observatory operated. The choice of Ceres was appropriate in many ways, for the grain goddess was said to have made Sicily her special domain, and the island's fertile fields had fed Rome during the days of the Republic and Empire. The addition of Ferdinandia was a gesture of political prudence and genuine gratitude, an acknowledgement of the royal support that had made the Palermo Observatory possible. In time, the second part of the name would fall away, as such honorifics often do, and the object would be known simply as Ceres, a name that it carries to this day. The discovery of Ceres marked the beginning of a new chapter in astronomical history, though Piazzi himself could not have foreseen all that would follow. The object he had found on that quiet New Year's night would prove to be neither a comet nor a proper planet, but something in between, the first of a new class of celestial bodies that would come to be called asteroids or minor planets. In the years that followed, other observers would find more such objects in the same region of space, populating the gap between Mars and Jupiter with a swarm of small rocky worlds that the ancients had never imagined. But all of that lay in the future as Piazzi set down his pen and looked out over the rooftops of Palermo, uncertain whether his careful observations would prove to be a footnote in the history of astronomy or the opening page of an entirely new volume. For now, the immediate challenge was a practical one, the challenge of finding Ceres again once it emerged from the glare of the sun, a task that would prove far more difficult than anyone anticipated, and would require the intervention of one of the greatest mathematicians of the age. But that story belongs to another night and another telling, and for the moment we may rest content with the image of Giuseppe Piazzi, Theatine monk and patient observer of the heavens, recording in his neat hand the positions of a wandering point of light that would one day bear the name of an ancient goddess, moving slowly and steadily through the winter stars above the island of Sicily. And so we come now to a rather quiet sort of crisis, the kind that unfolds not with thunder or spectacle but in the slow accumulation of worried letters between astronomers, in the gradual realization that something precious had been found and then, through no fault of anyone in particular, had slipped away into the vastness of the sky. Giuseppe Piazzi, as you may recall, had observed his new object on 24 separate nights between the 1st of January and the 11th of February in 1801, and during that time he had watched it move, ever so slowly, against the fixed stars. But the sun, as it does each year, continued its apparent journey along the ecliptic, and by early February it was drawing uncomfortably close to the region of sky where Ceres wandered. The twilight crept earlier each evening, and the little point of light that Piazzi had been tracking grew fainter and fainter in the brightening sky, until at last it was swallowed entirely by the solar glare, and there was nothing more to be done but wait. This is a perfectly ordinary occurrence in astronomy, this losing of objects behind the sun, and under normal circumstances it would pose no great difficulty. One simply calculates where the object will be when it emerges on the other side, points the telescope at that location some months later, and there it is, faithfully continuing along its path. But Ceres was not an ordinary circumstance, and the astronomers of Europe found themselves in a rather awkward position. To calculate where a celestial body will be in the future, you must first determine its orbit. And to determine an orbit with any confidence, you generally need observations spanning a considerable arc of the sky, ideally covering a significant portion of the object's journey around the Sun. The traditional methods, refined over centuries for calculating the paths of comets and planets, required data collected over many months, sometimes years, showing the object in widely separated positions so that the shape and orientation of its orbit could be properly deduced. What Piazzi had provided was something far more limited. His observations covered just 41 days, and during that brief window, Ceres had moved through a mere 3 degrees of arc against the background stars. 3 degrees is a very small angle indeed, roughly the width of 6 full moons laid side by side, and from such a tiny sample of motion, the astronomers were being asked to extrapolate an entire orbit, to predict where this object would be not in a few days or weeks, but many months hence, after it had traveled unseen through a substantial portion of its path around the Sun. The challenge was rather like being shown a single short curve drawn on an enormous sheet of paper and being asked to deduce the complete shape of the figure, whether it might be a circle or an ellipse, how large it might be, and precisely where any given point along its circumference might fall. Several astronomers attempted the calculation using the established methods of the time, and their results, while earnest, were troublingly varied. The predicted positions disagreed with one another by considerable margins, and none of the calculators could claim any great confidence in their figures. The difficulty was not merely technical but fundamental. The existing techniques for orbit determination had been developed for situations with abundant data, and they simply were not designed to extract reliable information from such a meager sample. As the months passed and Ceres remained hidden behind the Sun, a quiet anxiety settled over the astronomical community. The first new object to be found in the gap between Mars and Jupiter, this potential missing piece of the celestial puzzle, might be lost forever, not through any failure of observation but through a failure of mathematics. It was at this juncture that a young mathematician in the Duchy of Brunswick turned his attention to the problem. Carl Friedrich Gauss was 24 years old in 1801, a prodigy who had already made remarkable contributions to number theory and pure mathematics, but who had not yet applied his formidable abilities to the practical problems of astronomy. Gauss lived in modest circumstances, supported by a small stipend from Duke Ferdinand of Brunswick, who had recognized the young man's extraordinary gifts and provided him with the means to pursue his studies without the immediate pressure of employment. In his quiet rooms, Gauss worked through mathematical problems with an intensity and rigor that few could match, and when he learned of the Ceres dilemma, he recognized it as precisely the sort of challenge that suited his particular talents. The problem, as Gauss understood it, was not merely one of applying existing methods more carefully, but of developing entirely new mathematical tools capable of extracting the maximum possible information from the limited available data. Over the course of just a few weeks in the autumn of 1801, Gauss accomplished something rather remarkable, working with a concentration that allowed him to make progress that might ordinarily take years. He developed what he called the method of least squares, a technique for finding the best possible estimate of unknown quantities when the observations themselves contain small errors. Every measurement made by an astronomer, no matter how skilled, contains some degree of imprecision, tiny uncertainties introduced by the atmosphere, by the instruments, by the limitations of human perception, And when you have many such measurements and wish to find the values that best account for all of them simultaneously, the method of least squares provides a principled way to do so, minimizing the overall disagreement between the predicted and observed positions. But Gauss went further still. He developed new techniques specifically suited to the problem of determining an orbital path from a short arc of observations, methods that made clever use of the mathematical relationships governing elliptical orbits to constrain the possible solutions. Where others saw too little information to draw reliable conclusions, Gauss perceived hidden structure, ways to squeeze meaning from those 41 nights of careful watching. He worked with remarkable speed, his calculations filling page after page, and by September of 1801 he had arrived at a prediction for where Ceres would reappear when it finally emerged from behind the Sun. Franz Xaver von Zach, whose journal, the Monatliche Korrespondenz, had become the central forum for astronomical communication in Europe, published Gauss's prediction in the September 1801 issue. The young mathematician from Brunswick had provided precise coordinates, indicating the region of sky where observers should direct their telescopes when Ceres became visible once more. Other predictions existed as well, calculated by other astronomers using other methods, and there was considerable variation among them, a spread of several degrees representing the genuine uncertainty about where this elusive object might be found. The astronomical community could do nothing but wait, watching the calendar as autumn turned toward winter, and the geometry of Sun and Earth slowly shifted to bring the region of Ceres's presumed location into the dark night sky once more. The wait must have been rather trying for those who cared about such things, which is to say, for nearly every serious astronomer in Europe. Months had passed since anyone had seen Ceres, and during that time the little body had continued its silent journey, invisible and unchecked, following whatever path the laws of gravity prescribed. If the predictions were wrong, if Ceres were not where the calculators said it would be, then the search would become vastly more difficult, perhaps impossible, for one cannot scan the entire sky hoping to stumble upon a faint point of light that looks much like any other star. The predictions mattered enormously, and yet there was nothing to do but trust the mathematics and point the telescopes where the numbers indicated. December came, and with it, the anxious scanning of the predicted positions began. It was von Zach himself, observing from Gotha, who first recovered the lost object, spotting Ceres on the 7th of December, 1801, very near the position that Gauss had calculated. The relief and satisfaction this must have occasioned can well be imagined, though we shall not dwell on the emotional dimensions of the moment. What matters for our purposes is the sober fact that the prediction had worked, that the mathematics had proved sound, and that Ceres was back within the grasp of human observation. Von Zach confirmed his sighting on subsequent nights, verifying that the point of light he had found was indeed moving against the stars in the manner expected of the lost object. And then, just a few weeks later, came a discovery that must have seemed almost poetic in its timing. On the 1st of January, 1802, exactly 1 year to the day after Piazzi had first spotted the unknown object from Palermo, the German astronomer Heinrich Wilhelm Olbers independently recovered Ceres from his observatory in Bremen. Olbers had been searching the predicted region as well, and his confirmation removed any lingering doubt. Ceres had been found, lost, and found again, completing a full circuit not only around a portion of its orbit but through the annual calendar of human reckoning. Most remarkably of all, when the observed position of Ceres was compared with the various predictions that had been published, Gauss's calculation proved by far the most accurate. Ceres was found within half a degree of where the young mathematician had said it would be, a stunning vindication of his new methods. Half a degree is approximately the width of the full moon as seen from Earth, and considering that Ceres had been tracked for barely 3 degrees of arc before being lost, and that it had travelled unseen through many months and many degrees of its orbit before being recovered, this level of precision was extraordinary. The other predictions had been off by considerably larger margins, and some had missed the mark so badly that their authors must have felt a certain quiet embarrassment, though the scientific community was generous in its acknowledgement that the problem had been genuinely difficult. The recovery of Ceres established Gauss's reputation almost overnight. Here was a young man, scarcely past his student years, who had solved a problem that had vexed the leading astronomers of Europe, and he had done so not through lucky guessing but through the development of genuinely new mathematical techniques. The method of least squares alone would have been a significant contribution, and it has since become one of the most widely used tools in all of science, applied whenever one wishes to find the best fit to imperfect data. But Gauss's work on orbital determination was equally important, providing astronomers with a powerful set of methods for calculating the paths of newly discovered objects, methods that would prove essential as more and more bodies were found in the years and decades to come. Gauss continued to refine and extend his techniques, and in 1809 he published his comprehensive treatise on the subject, titled Theoria Motus Corporum Celestium in Sectionibus Conicis Solem Ambientium, which translates roughly as Theory of the Motion of Heavenly Bodies Moving About the Sun in Conic Sections. This work gathered together all of his methods for orbit calculation, presenting them in a systematic and rigorous form that other astronomers could study and apply. It became the standard reference for orbital mechanics, consulted and admired for generations, and it cemented Gauss's position as one of the foremost mathematicians and astronomers of his age. The young man who had worked through his calculations in quiet rooms in Brunswick, supported by the modest patronage of a German duke, had become a figure of international renown, and his methods would guide the discovery and tracking of celestial objects for more than a century to come. There is something rather comforting, perhaps, in this story of loss and recovery, in the knowledge that even when an object disappears from view, the careful application of mathematical reasoning can predict its return. The sky is vast, and the objects within it are many, and yet they move according to laws that human minds can comprehend and human calculations can capture. Ceres had been found, lost behind the glare of the sun, and found again, exactly where the mathematics said it would be. The methods that enabled this recovery would soon be put to use again, for the gap between Mars and Jupiter had more surprises in store, and the astronomers of Europe were only beginning to understand what they had discovered. In the quiet months that followed the recovery of Ceres, the astronomical community had begun to settle into a new understanding of the solar system, one that now included a small and distant body circling the Sun between Mars and Jupiter, right where the curious mathematics of the Titius-Bode law had suggested something ought to be. The observers across Europe had done their work with care and patience, following the faint point of light as it moved against the fixed stars, and the calculations of the young mathematician Gauss had proven their worth beyond any reasonable doubt. Ceres was real. It was there, and it seemed to complete a pattern that had long whispered of a missing world. And so the astronomers might have been forgiven for believing that this particular chapter of discovery had reached its natural conclusion, that the gap in the planetary sequence had been filled, and that the heavens had yielded their secret. But the universe, as it so often does, had more to reveal, and the next revelation would come from an unexpected quarter, from a rooftop in Bremen, and from a man who spent his daylight hours not in an observatory but attending to the ailments of his fellow citizens. Heinrich Wilhelm Mathers Olbers was born in the year 1758, in the small town of Aarbergen near Bremen, in what was then part of the Holy Roman Empire, and from his earliest years he displayed a gentle curiosity about the natural world that would shape the course of his long and productive life. He studied medicine at the University of Göttingen, where he received thorough training in the healing arts, and he established himself as a physician in Bremen in 1781, building a practice that would serve the community for decades to come. His patients knew him as a kind and attentive doctor, one who listened carefully and prescribed thoughtfully, and his reputation as a healer grew steadily throughout the city. But what his patients may not have fully appreciated, at least not at first, was that their physician harbored a passion that occupied his nights and his thoughts in equal measure to his medical work. For Olbers was, in the truest sense, a devoted amateur astronomer, and the roof of his house in Bremen had been converted into a modest but effective observatory, equipped with the instruments he needed to pursue his celestial investigations. The arrangement was not unusual for the time, when the boundaries between professional and amateur science were far more permeable than they would later become, and when a dedicated observer with good equipment and careful habits could contribute meaningfully to the advancement of knowledge. Olbers had already made a name for himself in astronomical circles through his work on comets, developing in 1797 a new and efficient method for calculating their orbits that was widely adopted by his peers. He was a corresponding member of the Celestial Police, that informal network of observers who had pledged to search for the missing planet, and he had participated in the efforts to recover Ceres after Piazzi's initial observations. His equipment was not elaborate by the standards of the great observatories, but it was sufficient for the work he wished to do, and his skill as an observer was considerable. Night after night, after his medical duties were complete and his household had settled into the quiet rhythms of evening, Olbers would climb to his rooftop perch and turn his telescope toward the stars, recording what he saw with the meticulous care that characterized all his endeavors. On the evening of the 28th of March in the year 1802, some 15 months after Piazzi's discovery of Ceres and only a few months after that object had been successfully recovered, Olbers was engaged in routine observations of the region of sky where Ceres was then located. This was careful work, the kind of patient watching that requires attention but not excitement, and Olbers moved his telescope slowly across the field, noting the positions of the stars he encountered and checking them against his charts. He was familiar with this patch of sky by now, having observed it many times in the preceding weeks, and he knew which points of light belonged there and which did not. And so when he noticed an unfamiliar object of the 7th magnitude, a faint but distinct point that had not been present in his earlier observations, his attention sharpened in that quiet way that experienced observers know so well. He noted its position carefully, recorded the time, and continued his watch. The object was not on any chart he possessed, and it did not correspond to any known star. It was, in the parlance of the hunt, a stranger in the field. Olbers observed the object again the following night, and the night after that, and each observation confirmed what the first had suggested. The stranger was moving. It drifted slowly against the background of fixed stars, shifting its position in a manner consistent with an object in orbit around the Sun, and its motion was not that of a comet, which would typically show a visible tail or a fuzzy appearance, but rather that of a small, solid body reflecting sunlight as it traced its path through the void. The implications were startling, even to a mind as methodical as that of Olbers. He was looking at a second object in very nearly the same region of space where Ceres had been found, another small world circling the Sun in the great gap between Mars and Jupiter. This was not what anyone had expected. The Titius-Bode law had suggested one missing planet, and Ceres had seemed to fill that role admirably. But here was another, and its existence raised questions that the prevailing theories could not easily answer. Olbers acted with appropriate haste, communicating his discovery to his colleagues in the astronomical community with the same efficiency that had marked his earlier work on comets. Word spread quickly through the network of observers, and within days telescopes across Europe were trained on the new object, which Olbers named Pallas, after the Greek goddess of wisdom and warfare, following the classical tradition that had governed the naming of planets since antiquity. The observations that followed confirmed Olbers's findings in every particular. Pallas was real. It was there, and it was moving in an orbit that placed it squarely in the territory that Ceres had so recently claimed for its own. The astronomical world found itself confronted with a puzzle of considerable depth, for the presence of two such objects in the same general region of space was difficult to reconcile with the existing understanding of planetary formation and the orderly architecture of the solar system. The orbital elements of Pallas, as they were refined through continued observation and calculation, added a further dimension of strangeness to the discovery. While Ceres moved in an orbit that was only modestly inclined to the plane of the ecliptic, the great circle that marks the apparent path of the Sun through the sky and along which the major planets more or less travel, Pallas proved to be a rebel of sorts, following a path that was tilted at an angle of some 34.8 degrees to that fundamental reference plane. This was unprecedented among the known members of the solar system. The major planets, from Mercury out to the distant reaches where Uranus traced its slow circuit, all kept relatively close to the ecliptic, their orbital planes deviating by no more than a few degrees. Pallas, by contrast, soared high above and plunged far below the plane that the other worlds observed with such apparent fidelity. Its orbit was also notably more elongated than that of Ceres, carrying it through a greater range of distances from the Sun and adding to the sense that this was an object of a fundamentally different character than the stately planets that had long been known. The discovery of Pallas prompted a flurry of observational activity, as astronomers sought to characterize this unexpected newcomer to the solar system. Among the most significant contributions to this effort came from William Herschel, the German-born British astronomer whose discovery of Uranus in 1781 had already secured his place among the giants of the field. Herschel possessed one of the finest telescopes then in existence, a great reflecting instrument of his own construction that gathered light with remarkable efficiency, and he turned this formidable apparatus toward both Ceres and Pallas in the spring of 1802. Seeking to determine their physical characteristics through careful observation. What he found, or rather what he did not find, would prove crucial to the developing understanding of these mysterious objects. When Herschel examined Ceres and Pallas through his telescope, he found that neither object presented a visible disk of the sort that the major planets displayed. Mars, Jupiter, Saturn, and even distant Uranus all showed themselves as tiny but perceptible circles of light when viewed through a sufficiently powerful instrument, their angular sizes reflecting their substantial dimensions and their relative proximity to Earth at various points in their orbits. But Ceres and Pallas, despite Herschel's best efforts, remained stubbornly point-like, appearing as nothing more than bright specks indistinguishable in form from the fixed stars that surrounded them. They showed no cometary features, no fuzzy halos or streaming tails that might suggest they were composed of volatile ices boiling away under the sun's heat. They were simply points of light, star-like in their appearance, moving against the stellar background with the steady patience of bodies bound to solar orbits. This observation led Herschel to a significant conclusion regarding the size of these objects. If Ceres and Pallas showed no visible disk even through his powerful telescope, then they must be far smaller than any of the known planets, too small for their angular extent to be resolved at the distances from which they were being observed. Herschel attempted to estimate their dimensions based on their brightness and his assumptions about their reflectivity, arriving at figures that placed them in the range of a few hundred miles across, far smaller than even the smallest planet and scarcely deserving of the planetary title that had initially been applied to Ceres. These estimates would later prove to be roughly correct, though the methods of the time could not achieve great precision in such measurements, and they reinforced the growing sense that Ceres and Pallas represented a category of celestial object quite distinct from the planets proper. It was Herschel who proposed a new term for these peculiar bodies, a word that would capture their essential character as observed through the telescope. In a paper presented to the Royal Society in May of 1802, he suggested that they be called asteroids, a name derived from the Greek word meaning star-like, in recognition of their point-like appearance even under the highest magnification. The term was elegant and descriptive, acknowledging the way these objects resembled stars to the eye while distinguishing them from the true stars that remained fixed in their positions night after night. Not all of Herschel's contemporaries were immediately receptive to this nomenclature, and some continued to refer to Ceres and Pallas as planets or as planetoids for many years thereafter, but the word asteroid would eventually win broad acceptance and remains in use to this day, a lasting legacy of Herschel's careful thinking about the nature of these curious wanderers. The existence of two such objects in the same general region of space demanded explanation, and it was Olbers himself who proposed the hypothesis that would dominate discussion of the asteroids for decades to come. Struck by the proximity of the orbits of Ceres and Pallas, and by the apparent coincidence of finding two small bodies where theory had predicted one larger world, Olbers suggested that both objects might be fragments of a single planet that had once occupied this region of the solar system but had suffered some catastrophic destruction in the distant past. This exploded planet hypothesis, as it came to be known, offered a tidy explanation for the otherwise puzzling multiplication of objects in the zone between Mars and Jupiter. If a primordial planet had been shattered, whether by internal forces or by collision with some other body, then its debris would naturally scatter into a variety of orbits, all more or less centered on the original planetary distance from the Sun. The peculiar inclination of Pallas's orbit, so different from that of Ceres, could be understood as a consequence of the violence of the disruption, which might have flung fragments in many different directions. The exploded planet hypothesis was attractive in its simplicity and its explanatory power, and it suggested a testable prediction, namely that additional fragments might yet be found if observers continued to search the region where Ceres and Pallas had been discovered. Olbers himself took up this search with renewed energy, and he was not alone in doing so. The discovery of Pallas had demonstrated that the heavens might yet hold surprises, that the work of cataloguing and understanding the solar system was not yet complete, and that patient observation might continue to yield discoveries of real significance. And so the astronomers watched, night after quiet night, their telescopes turned toward the dark spaces between the stars, their eyes adapted to the dim light, their minds open to whatever the universe might choose to reveal. The golden age of asteroid discovery had truly begun, though those who lived through it could not yet know just how rich the harvest would prove to be, nor how profoundly their understanding of the solar system would be transformed by what lay ahead. And so we come now to the third and fourth of these small wandering worlds, discovered in the years 1804 and 1807 respectively, and in learning of their finding we shall meet two more patient observers whose names deserve to rest gently in our memory as we settle deeper into the quietness of the evening. You may recall from our earlier telling that Johann Schroeder had established at Lilienthal, not far from Bremen in northern Germany, a modest but earnest observatory, and that from this place he had helped to organize that loose fellowship of astronomers who called themselves, with a certain hopeful grandeur, the Celestial Police. These watchers of the zodiac had divided the sky into portions, each member taking responsibility for a particular region, and they had set about their methodical work of searching for whatever small planet might be hiding in the darkness between Mars and Jupiter. It is a gentle irony, and one worth noting as your eyes grow heavy, that although this organized effort brought together some of the finest observers of the age, the first two asteroids had been found not by the police themselves but by others working independently, Piazzi stumbling upon Ceres quite by accident and Olbers finding Pallas while making observations related to the first discovery. But the third asteroid, the one we shall speak of now, was indeed discovered by a proper member of this celestial constabulary, and his name was Carl Ludwig Harding, and he found his small prize on the first day of September in the year 1804, working quietly at Schroeder's own observatory in Lilienthal. Harding was born in 1765 in the town of Lauenburg, which sits along the Elbe River in what was then the Duchy of Lauenburg, and he had come to astronomy through the gentle pathway of mathematics and natural philosophy. He was not a wealthy man, nor did he possess the resources to construct or acquire the grand instruments that some of his contemporaries enjoyed. When Schroeder invited him to serve as an assistant at the Lilienthal Observatory, Harding accepted gratefully, and it was there that he took up the patient work of scanning the heavens for any small body that might betray itself through motion against the fixed stars. The telescope that Harding used in his discovery was a modest instrument indeed, a refractor with an aperture of only 2.5 inches, which is to say approximately 63 millimeters in diameter. This was not a large telescope even by the standards of that era, when the great reflectors of William Herschel boasted apertures of 18 inches and more. But Harding understood, as all careful observers come to understand, that the size of one's instrument matters less than the patience and thoroughness with which one uses it, and that a small telescope wielded with dedication may reveal what a larger one misses through haste or inattention. His method of searching was built upon the careful preparation of star charts, and this is a technique worth describing as you lie there listening, for it captures something of the quiet diligence that characterized so much of the astronomical work of this period. Harding would select a region of the sky within the zodiacal band, that strip of celestial territory through which the planets are known to wander, and he would make a detailed drawing of all the stars visible in that region through his small telescope. Then, on subsequent nights, he would return to the same region and compare what he saw with what he had recorded, looking for any point of light that had shifted its position or that appeared where none had been marked before. This chart-based method required no complex calculations, no mathematical predictions of where a planet ought to be found. It asked only that the observer be willing to sit for long hours at the eyepiece, recording faithfully what was seen, and then to sit for long hours more on following nights, comparing and checking. It was work that suited Harding's temperament, and he pursued it with the steady persistence of one who finds satisfaction in thoroughness rather than in speed. On that September night in 1804, Harding was examining a region of the sky in the constellation of Pisces when he noticed a small point of light that did not correspond to any star on his chart. He noted its position carefully and returned the following night to find that it had moved, just slightly, against the background of fixed stars. Here was the telltale sign of a planetary body, and Harding continued his observations over the following nights until he was satisfied that he had indeed found a new member of the solar family. The announcement of this discovery brought a quiet satisfaction to the members of the celestial police, for it demonstrated that their organized approach could bear fruit, even if their first successes had come through the efforts of observers outside their ranks. The new body was given the name Juno, after the queen of the Roman gods, the wife of Jupiter himself. This naming followed the pattern established with Ceres and Pallas, drawing upon the classical mythology that educated Europeans of that era knew so well. Juno had been the goddess of marriage and childbirth, the protector of the Roman state, and her name carried associations of dignity and importance that seemed fitting for a new celestial discovery. Harding continued his work at Lilienthal and later moved to Göttingen, where he became a professor of astronomy and where he spent many years preparing a comprehensive atlas of the stars. His discovery of Juno remained the high point of his observational career, and it ensured that his name would be remembered long after the details of his daily work had faded from memory. But for our purposes this evening, what matters most is the image of that patient man with his small telescope and his careful charts, working night after night in the quietness of the Lilienthal Observatory, finding at last the small wandering world that others had sought in vain. Now we come to the fourth asteroid, and to the man who found it, who was none other than Heinrich Wilhelm Olbers, the Bremen physician we met earlier in our narrative, the same Olbers who had discovered Pallas just 2 years before Harding found Juno. Olbers, you will recall, had proposed a theory to explain the existence of these small bodies between Mars and Jupiter. He suggested that they might be fragments of a larger planet that had once occupied that region of space but had been destroyed by some ancient catastrophe, perhaps an internal explosion or the impact of a comet. This theory, while eventually superseded by other explanations, had a certain logical appeal at the time, and it made a specific prediction that Olbers found intriguing. If the asteroids were indeed fragments of a single shattered world, then their orbits should all pass through the point in space where the original planet had broken apart. By identifying where the orbits of Ceres and Pallas intersected, Olbers believed he might find a promising region in which to search for additional fragments. And so, in the years following his discovery of Pallas, Olbers turned his telescope again and again to those regions of the sky where a fragment following such an orbit might be expected to appear. He searched with the same patience that characterized all his astronomical work, fitting his observations into the hours when his medical practice allowed, peering through his telescope from the upper floors of his house in Bremen while the city slept below. On the 29th of March in 1807, his patience was rewarded. In the constellation of Virgo, Olbers found a small point of light that moved against the stars in the manner of a planetary body. He followed it for several nights to confirm its nature, and then announced to the astronomical world that a fourth asteroid had been discovered. This new body was remarkable in one particular respect that set it apart from its 3 predecessors. It was brighter, considerably brighter, than any of the others. While Ceres and Pallas and Juno required a telescope to be seen, this fourth asteroid reached a maximum brightness of approximately magnitude 5.5, which placed it just within the range of visibility for a keen-eyed observer on a clear dark night. This meant that, under ideal conditions, the new asteroid could be glimpsed without any optical aid at all, a naked-eye object hiding among the thousands of stars that sprinkle the night sky. The brightness of this fourth asteroid was due to a combination of factors, including its size, which was substantial compared to the others, and the reflective properties of its surface, which turned out to be unusually efficient at bouncing sunlight back toward Earth. Later measurements would show that this body reflects roughly 40% of the light that falls upon it, making it one of the most reflective objects in the asteroid belt. Though of course such precise measurements lay far in the future from the perspective of Olbers and his contemporaries. The naming of this fourth discovery fell to Carl Friedrich Gauss, the brilliant mathematician who had done so much to enable the recovery of Ceres and who had calculated the orbits of all these small bodies with such remarkable precision. Gauss suggested the name Vesta, after the Roman goddess of the hearth, the keeper of the sacred flame that burned in her temple and that symbolized the warmth and security of the home. It was a gentle name, a domestic name, appropriate perhaps for an object that could be seen, at least occasionally, without the intervention of telescopes or observatories, simply by standing outside one's own home and looking up at the sky. And now, as we settle further into the quietness of this account, we must note something rather curious about what happened next, or rather, what did not happen next. After the discovery of Vesta in 1807, no new asteroids were found for a very long time indeed. The fifth asteroid, which would eventually be named Asteroid, was not discovered until 1845, a gap of 38 years during which the known population of these small worlds remained fixed at 4. This long pause requires some explanation, and there were several factors that contributed to it. One consideration was the simple matter of interest and motivation. When Piazzi found Ceres, the discovery had caused great excitement because it seemed to confirm the prediction of a missing planet between Mars and Jupiter. When Olbers found Pallas, the excitement had continued because it suggested something unexpected and strange about the nature of this region of the solar system. Juno and Vesta added to the catalogue, and each discovery was duly celebrated. But by 1807, the novelty had begun to fade, and the astronomical community found itself uncertain about how to interpret what had been found. Olbers's theory of an exploded planet provided one framework for understanding, and if that theory were correct, it suggested that there might be only a limited number of major fragments to be discovered. Perhaps, some astronomers speculated, the 4 bodies already known represented the principal pieces of the shattered world, and any remaining fragments would be too small and faint to detect. This reasoning, while ultimately mistaken, was not unreasonable given the evidence available at the time, and it dampened enthusiasm for continued searching. There was also the practical matter of how difficult such searching was. Without the photographic techniques that would later revolutionize asteroid detection, finding these small bodies required the same laborious chart-based methods that Harding had employed. Long nights of careful observation and comparison, with no guarantee of success. The astronomers who had formed the Celestial Police gradually turned their attention to other projects, other questions, other areas of the sky where discoveries might come more readily. The Lilienthal Observatory itself suffered a sad fate during this period. When Napoleon's forces occupied the region in 1813, the observatory was damaged and eventually destroyed, its instruments scattered or lost. Schroeder died the following year, his life's work in ruins, and with him passed the institutional heart of the asteroid hunting enterprise. And so the asteroids waited, those countless small worlds drifting silently in their orbits, unknown and unsought, while the years passed and the generations of astronomers turned their attention elsewhere. Ceres and Pallas and Juno and Vesta traced their paths around the sun, occasionally brightening enough to be glimpsed by those who knew where to look, but revealing nothing of the thousands of companions that shared their realm. It would take new observers, new techniques, and a renewed sense of curiosity before the search would resume. But that story belongs to another section of our narrative. For now, let us rest with the knowledge that 4 small worlds had been found, that they had been named for goddesses of harvest and wisdom and marriage and the hearth, and that they circled patiently in the darkness between Mars and Jupiter, waiting for the time when human eyes would seek them out once more. After the discovery of Vesta in the spring of 1807, and despite the continued vigilance of skilled observers across Europe, no new asteroid would be found for nearly 4 decades. This long interval of silence, stretching from 1808 all the way to 1845, represents one of the more curious pauses in the history of astronomical discovery, a period during which the celestial police, as they had come to be known, gradually disbanded and turned their attention elsewhere, and during which the wider astronomical community came to accept, with quiet certainty, that only 4 minor planets existed in the space between Mars and Jupiter. It was not that astronomers had lost interest in the heavens, for this period witnessed remarkable achievements in other areas of celestial science, but rather that the particular challenge of finding small, faint, slowly moving points of light among the countless stars had proven more difficult than anyone had anticipated, and the tools and methods of the early 19th century were simply not equal to the task. Heinrich Olbers, who had discovered both Pallas and Vesta and who had proposed the provocative theory that these bodies were fragments of a destroyed planet, continued his searches with admirable persistence well into the 1820s. Night after night, when the skies over Bremen were clear and his medical practice permitted, he would return to his observatory and sweep methodically through the regions of the zodiac where asteroids might reasonably be expected to appear. He knew the constellations intimately, had committed thousands of star positions to memory, and possessed the patience that asteroid hunting demanded. Yet year after year his searches yielded nothing new. The asteroids, it seemed, were hiding themselves among the stars with frustrating effectiveness, and without comprehensive charts showing the precise positions of fainter stars. Even the most dedicated observer could not be certain whether a given point of light was a familiar star or an unfamiliar wanderer. Olbers eventually turned his attention to other matters, including the famous paradox that still bears his name concerning why the night sky is dark, and by the late 1820s, the systematic search for new asteroids had largely ceased. The reasons for this long hiatus were both technological and sociological, reflecting the limitations of early 19th century instruments as well as the shifting priorities of the astronomical community. The telescopes of this era, while beautifully crafted and capable of revealing considerable detail on planetary surfaces and in certain types of celestial objects, suffered from relatively narrow fields of view, which made the systematic surveying of large areas of sky a laborious and time-consuming undertaking. A typical refractor of respectable aperture might show only a small fraction of a degree in its eyepiece, meaning that an astronomer wishing to examine a particular region of the zodiac would need to make hundreds or even thousands of individual pointings, carefully noting the position and brightness of every star-like object in each field, and comparing these observations against existing charts. The process was tedious beyond description, required exceptional concentration and record-keeping, and offered no guarantee of success even after months or years of dedicated effort. Moreover, the star charts available during the early decades of the 19th century were incomplete in ways that made asteroid detection particularly challenging. While excellent catalogues existed for the brighter stars, the fainter objects that populated the background against which asteroids moved were often poorly documented or entirely absent from the available references. An astronomer might notice a faint point of light in the eyepiece and find it missing from a chart, But this did not necessarily indicate a new discovery, for it might simply be a star too faint to have been recorded in previous surveys. Without photographic plates, which would not become available for astronomical purposes until later in the century, there was no way to create permanent records of star fields that could be examined at leisure and compared systematically over time. Every observation had to be made in real time, with the human eye as the only detector, and the mental effort required to hold the appearance of a star field in memory while comparing it against a printed chart was considerable. During these dormant decades, astronomical attention turned toward problems that seemed more tractable with existing technology and that promised more immediate rewards. The study of double stars, those pairs of stars that appear close together in the sky and that in many cases are physically bound to one another by gravity, attracted considerable interest during this period, and Wilhelm Struve at the Dorpat Observatory in Estonia undertook a monumental survey that would eventually catalogue thousands of these systems. Using the excellent Fraunhofer refractor installed at Dorpat in 1824, one of the finest telescopes then in existence, Struve measured the positions and separations of double star pairs with unprecedented precision, work that would prove important for understanding stellar distances and motions. His great catalogue of double stars, published in 1827, represented years of painstaking observation and demonstrated what could be achieved through sustained attention to a well-defined astronomical problem. The measurement of stellar parallax, the tiny apparent shift in a star's position caused by Earth's motion around the Sun, represented another grand challenge that occupied the best observers of this era. Astronomers had sought to detect this shift since the time of Copernicus, for its measurement would provide direct confirmation of Earth's orbital motion and would allow the distances to the stars to be determined for the first time. The difficulty lay in the extreme smallness of the effect, even for the nearest stars, and the extraordinary precision required to detect it against the background of atmospheric disturbance and instrumental imperfection. Friedrich Wilhelm Bessel, working at the Königsberg Observatory in Prussia, finally succeeded in measuring the parallax of the star 61 Cygni in 1838, using a specialized instrument called a heliometer that allowed positions to be measured with unparalleled accuracy. This achievement, announced the same year that similar measurements were reported by Friedrich Struve for the star Vega and by Thomas Henderson for Alpha Centauri, marked a turning point in our understanding of the scale of the universe and demonstrated the power of precision positional astronomy. The heliometer that Bessel employed in his parallax work was a remarkable instrument, consisting essentially of a telescope whose objective lens had been cut in half, with each half mounted so that it could be moved independently along the direction of the cut. By adjusting the relative positions of the two half lenses, an observer could bring the images of two stars into apparent coincidence, and the amount of adjustment required provided an extremely precise measure of their angular separation. This technique, originally developed for solar observations where it was used to measure the Sun's apparent diameter, proved ideally suited to the measurement of small angles and represented the highest achievement of pre-photographic positional astronomy. The filler micrometer, another precision measuring device that used fine threads or wires positioned in the telescope's focal plane, also reached new levels of refinement during this period, allowing observers to measure the positions of stars and other objects with an accuracy that would have astonished astronomers of earlier generations. The development of improved star charts during these decades would prove crucial for the eventual resumption of asteroid hunting, even though this was not their primary purpose at the time. Bessel, recognizing the importance of accurate stellar positions for all branches of observational astronomy, proposed in 1825 that the Berlin Academy of Sciences undertake the creation of a new set of star maps covering the zodiacal regions through which the Sun, Moon, and planets passed. These maps, which came to be known as the Berlin Academic Star Charts, were intended to show all stars down to the 9th or 10th magnitude, far fainter than any previous systematic survey, and to do so with positional accuracy sufficient for the most demanding astronomical work. The project was distributed among multiple observatories, with different institutions taking responsibility for different sections of the sky, and though progress was slow due to the enormous scope of the undertaking, the charts that eventually emerged would transform the practice of asteroid astronomy. The nebulae, those fuzzy patches of light scattered across the sky whose nature remained deeply uncertain, also attracted considerable attention during this period. William Herschel had catalogued many hundreds of these objects during his great surveys of the late 18th century, and his son John Herschel continued this work, eventually traveling to the Cape of Good Hope in South Africa to survey the southern skies that were invisible from European latitudes. The question of whether nebulae were truly gaseous in nature or merely appeared fuzzy because they consisted of vast numbers of stars too faint and too close together to be resolved individually remained a matter of active debate, and telescopes of increasing size and optical quality were brought to bear on the problem. This was astronomy of grandeur and philosophical significance, raising questions about the structure and extent of the universe that seemed more profound, to many observers, than the prosaic task of cataloguing additional chunks of rock orbiting between Mars and Jupiter. Comets, those spectacular visitors with their luminous tails and unpredictable appearances, dominated popular astronomical interest during the dormant decades and provided the general public with celestial spectacles far more dramatic than any asteroid could offer. The Great Comet of 1811, which became visible to the naked eye in the spring of that year and remained observable for an astonishing 9 months, attracted worldwide attention and was considered by many to be an omen of the tumultuous events then shaking Europe. Its tail stretched across a substantial portion of the sky at maximum extent, and it was bright enough to be seen easily in twilight, making it accessible to observers who had never looked through a telescope and who knew nothing of technical astronomy. The return of Halley's comet in 1835, precisely as predicted by the calculations that Edmund Halley had made more than a century earlier, provided a different kind of spectacle, one that demonstrated the power of Newtonian physics to forecast celestial events, and that drew enormous public interest to the astronomical enterprise. Throughout this long interval, the scientific consensus held that only 4 asteroids existed, a view that seemed increasingly confirmed with each passing year of unsuccessful searching. Ceres, Pallas, Juno, and Vesta were duly tracked in their orbits, their positions calculated and tabulated in the almanacs, their physical properties studied as best the instruments of the era would allow. They were given full planetary status in most astronomical references, bringing the total number of planets in the solar system to 11, and they were discussed in textbooks as established members of the celestial family, rather than as representatives of a larger population waiting to be discovered. Some astronomers wondered whether additional bodies might exist in the gap between Mars and Jupiter, but as the years passed without any new findings, such speculation came to seem increasingly theoretical, and the practical astronomical community devoted its energies to problems that offered more promising returns on investment. The lack of discoveries during these decades was not a failure of astronomical skill or dedication, but rather reflected the fundamental difficulty of the task and the limitations of available technology. Finding a new asteroid required an observer to notice a faint point of light, typically of the 8th or 9th magnitude, that moved slowly against the background of fixed stars, and to distinguish this motion from the countless observational errors and catalogue omissions that might otherwise explain an unfamiliar object. Without comprehensive charts of the faint stars, without photographic methods to record and compare sky fields, and without the time and resources to conduct sustained systematic searches. Even the most talented observers could search for years without success. The asteroids were there, orbiting silently in the darkness between Mars and Jupiter, but they would remain hidden until better tools and methods emerged to reveal them, and until a new generation of observers took up the challenge that Olbers and his contemporaries had reluctantly set aside. In the quiet town of Dresden, a small postal community nestled in the eastern reaches of Prussia, in a region that would one day become part of Poland and bear the name Dresdenko, there lived a man whose patience would eventually reshape our understanding of the solar system, and whose dedication would prove that the cosmos belongs not only to those with grand observatories and professional appointments, but also to those who simply look upward with care and persistence, night after night, year after year, asking nothing more than the chance to contribute something small and true to humanity's knowledge of the heavens above. Carl Ludwig Henke was born in 1793, and by the time he reached his middle years he had settled into the respectable but decidedly unglamorous profession of postmaster, a position that required him to sort letters and parcels, to manage the comings and goings of correspondence in a provincial town, and to conduct himself with the quiet reliability that such civil service demanded. And yet within this ordinary man there burned a gentle but unextinguishable flame of curiosity about the stars, a fascination that had taken root in his younger days and that he had never allowed to fade despite the mundane rhythms of his daily work. The year 1830 marked a turning point in Henke's life, though he could not have known at the time just how significant this moment would prove to be, for it was in that year that he made a decision that would occupy the next 15 years of his evenings and clear nights, a decision to search systematically for new minor planets in the region of sky where the four known asteroids traced their paths, that zone between Mars and Jupiter where Ceres, Pallas, Juno, and Vesta had been found in the brief flurry of discovery at the century's beginning, and where the trail had gone cold for what was then already approaching 3 decades. His equipment was modest in every sense of the word, consisting primarily of a small refracting telescope with an aperture of approximately 3.5 inches, built according to the excellent optical principles established by the renowned Bavarian craftsman Joseph von Fraunhofer, whose glass work had revolutionized the quality of telescopic lenses available to astronomers both professional and amateur. And though this instrument was a fine example of its type, it was nevertheless a far cry from the larger instruments employed at the major observatories of Europe, the sort of telescope that a comfortable middle-class enthusiast might acquire with careful saving, suitable for viewing the moon's craters and the rings of Saturn and the brighter deep sky objects, but requiring real skill and dedication to use for serious discovery work. Henke had no professional training in astronomy, no university credentials in mathematics or celestial mechanics, no appointment to any observatory or academy, and no colleagues with whom to share the long nights of careful observation. And yet he possessed something that proved equally valuable, perhaps more so in the context of his particular quest, and that was an almost inexhaustible reserve of patience combined with a methodical approach to his self-appointed task that never wavered across the years, a systematic dedication that saw him returning to his telescope whenever the skies were clear and his postal duties were complete, charting the positions of faint stars and watching for any subtle movement that might betray the presence of an undiscovered wanderer. The search for asteroids in this era was fundamentally a search for motion, for these small bodies revealed themselves not through any distinctive appearance, since through a telescope they looked exactly like stars, mere points of light without the fuzzy disks that characterize comets, but rather through their gradual drift against the fixed background of more distant stars over the course of nights and weeks. And so Henke would carefully note the positions of stars in a particular region of the zodiac, memorizing their arrangements or sketching rough maps, and then return on subsequent nights to see if any of these apparent stars had shifted position, a painstaking process that required extraordinary familiarity with the heavens and meticulous attention to detail. Year after year, Henke continued his patient vigil. Through the early 1830s, when the memory of Olbers and his generation was still fresh, through the middle years of that decade, when many had concluded that perhaps only 4 asteroids existed after all, through the late 1830s, when the search had been all but abandoned by the wider astronomical community, and into the 1840s, when the very concept of searching for new minor planets had come to seem rather quaint, a remnant of an earlier era's enthusiasm that had failed to yield further fruit. And yet through all of this the German postmaster persisted, neither discouraged by his lack of success nor deterred by the indifference of those who had long since turned their attention to other celestial questions. 15 years is a very long time to search for something without finding it. 15 winters watching the cold stars wheel overhead. 15 cycles of seasons during which the same familiar patterns rose and set, and during which countless nights of careful observation produced nothing more remarkable than an ever-deepening knowledge of the star fields themselves. And we might pause for a moment to appreciate the particular quality of determination this required. Not the dramatic persistence of someone facing immediate obstacles, but rather the quiet persistence of someone facing the slow erosion of hope that comes with years of patient effort and no reward. The gentle stubbornness of a soul that simply refuses to abandon a worthy endeavor merely because success has not yet arrived. And then, at last, on the 8th of December in the year 1845, during one of those long winter nights when the stars seem especially sharp and clear in the cold dry air, Carl Ludwig Henke noticed something that made his heart quicken with careful hope, a faint point of light that he could not account for in his mental catalogue of the region, a star that seemed to be where no star ought to be, and knowing the dangers of premature excitement, the frequency with which hopeful observers had mistaken ordinary stars for discoveries, he noted the position carefully and resolved to check again on subsequent nights to see if this mysterious point might reveal itself as something more than a fixed star after all. Over the following nights, as Henke returned to his small telescope and directed it once more toward the region of his potential discovery, the evidence accumulated with beautiful clarity, for the suspicious object had indeed moved. Not much, just the small but unmistakable drift that characterized a body orbiting the Sun at the distance of the asteroid belt. And Henke allowed himself to believe, with the cautious optimism of someone who has waited 15 years for precisely this moment, that he had at last succeeded in his long quest, that he had found a new member of the solar system, the 5th asteroid, ending a drought that had lasted 38 years since Heinrich Olbers had discovered Vesta on that spring evening in 1807. The announcement of Henke's discovery sent a wave of excitement through the astronomical community, a wave that seems almost surprising given how thoroughly interest in asteroid searching had faded during the intervening decades. But the very length of the gap made the new discovery all the more remarkable and newsworthy, and the fact that it had been achieved by an amateur with a small telescope rather than by a professional astronomer at a major observatory added a romantic quality to the story that captured the imagination of scientists and the public alike, proving that the cosmos still held secrets waiting to be uncovered by anyone with sufficient dedication and patience. The new asteroid was named Asteroid, following the tradition established with the first 4 minor planets of drawing upon the rich mythology of ancient Greece and Rome. And this name carried particular resonance, for Asteroid was the goddess of justice and innocence in classical mythology, the daughter of Zeus and the Mys according to some accounts, or of Astraeus and Eos according to others, and she was said to have been the last of the immortals to live among humanity during the Golden Age, eventually departing for the heavens when human wickedness became too great to bear. where she took her place among the stars as the constellation Virgo. And so there was a lovely appropriateness to naming a newly discovered celestial body after this figure who had once dwelt among mortals before ascending to her rightful place in the sky. The scientific establishment of Prussia took note of Henke's achievement in a most tangible way. For King Friedrich Wilhelm IV, recognizing the significance of the discovery and the extraordinary dedication it represented, awarded the amateur astronomer an annual pension of 300 thalers, a sum that would have been quite meaningful to a provincial postmaster, perhaps equivalent to a substantial portion of his regular salary. And this royal recognition served not only as personal reward for Henke's years of patient effort, but also as a public acknowledgement that valuable contributions to science could come from outside the traditional academic and institutional frameworks, that the universe was generous in revealing its secrets to those who sought them with sufficient care regardless of their formal credentials. But Henke's story did not end with Asteroid. For having at last tasted success after so many years of searching, he continued his observations with renewed vigor and perhaps with a more practiced eye, knowing now from direct experience exactly what he was looking for and what the subtle signs of discovery felt like. And this continued dedication bore fruit far more quickly than his initial search. For less than 2 years after finding Asteroid, on the 1st of July in 1847, Henke discovered yet another asteroid, the sixth to be identified, which was given the name Hebe after the Greek goddess of youth who served as cupbearer to the gods on Mount Olympus, pouring nectar for the immortals until she was eventually succeeded in that role by the beautiful Ganymede. This second discovery placed Henke in rather select company, for he became only the second person in history to discover more than one asteroid, sharing this distinction with Heinrich Olbers, who had found both Pallas and Vesta some 4 decades earlier. And in a sense Henke's achievement was even more impressive than that of his illustrious predecessor. For while Olbers had been a respected physician and astronomer with good equipment and the support of the scientific community during a period of active searching, Henke had worked in isolation with modest means during an era when most had given up hope of finding new minor planets at all. The impact of Henke's discoveries extended far beyond the mere addition of 2 more objects to the solar system's inventory, for his success demonstrated in the most practical terms possible that dedicated amateurs could make genuine contributions to astronomical knowledge, that one did not need a grand observatory or a university appointment or wealthy patrons to discover new worlds, but merely clear skies, a decent telescope, methodical habits, and above all the patience to continue searching even when success seemed impossibly distant. And this lesson would prove enormously influential in the years to come, inspiring a new generation of searchers who would soon transform the trickle of asteroid discoveries into a steady stream. The long drought had been broken. The spell of discouragement that had settled over asteroid astronomy since 1807 had been lifted, and suddenly it seemed possible again that more of these small bodies might be hiding in the spaces between the known objects, waiting to be found by anyone willing to look carefully enough. And this shift in perception, this renewed optimism about the possibilities of discovery, can be traced directly to the patient work of a German postmaster who refused to abandon his search despite 15 years of nightly disappointments, and who proved that sometimes the greatest contributions to human knowledge come not from brilliant flashes of insight, but from the quiet accumulation of countless hours of careful observation. In the years immediately following Henke's discoveries, other searchers would take up the quest with renewed enthusiasm, and the pace of asteroid discovery would accelerate dramatically. But those subsequent achievements would always owe something to the example set by Carl Ludwig Henke, the amateur who showed what dedication and patience could accomplish, who searched the cold winter skies from his small Prussian town year after year after year, asking nothing more than the chance to add one small truth to humanity's understanding of the heavens, and who eventually received from the cosmos the reward that such persistence deserves. Not once but twice, forever linking his name with the goddess of justice and the goddess of youth, Asteroid and Hebe, two small worlds circling endlessly between Mars and Jupiter, discovered by a postmaster with a modest telescope and an extraordinary gift for patient watching. The years following Carl Ludwig Henke's discovery of Asteroid in December of 1845 brought about a rather remarkable transformation in the pace of asteroid discovery, and what had once seemed an impossibly rare achievement, the identification of a new world among the countless fixed stars, gradually became something approaching a regular occurrence in the astronomical calendars of Europe. For nearly 4 decades, the 4 original asteroids had stood alone, their number seemingly complete, and many astronomers had quietly assumed that Ceres, Pallas, Juno, and Vesta represented the entirety of this curious class of objects orbiting between Mars and Jupiter. Henke's patient 15-year search had demonstrated otherwise, and his subsequent discovery of Hebe in July of 1847 confirmed that the region between the inner and outer planets contained more wandering bodies than anyone had previously suspected. The floodgates, as it were, had begun to open, and the trickle of new discoveries would soon become a steady stream that fundamentally altered how astronomers understood the architecture of our solar system. The acceleration of discoveries during this period owed much to a combination of improved observational tools, better reference materials, and a growing community of dedicated observers who recognized that the search for minor planets had become a legitimate and potentially fruitful area of astronomical research. Among the most productive of these new asteroid hunters was John Russell Hind, a young English astronomer working at George Bishop's private observatory in Regent's Park, London, who would contribute 3 new asteroids to the growing catalogue during these fertile years. Hind possessed a particular talent for the painstaking work of comparing observed star positions against chart references, and his keen eye and methodical approach made him exceptionally well suited to the detection of faint objects that moved imperceptibly against the fixed stellar background. The observatory where he worked, though situated in the increasingly light-polluted environment of the growing metropolis, benefited from excellent instrumentation and the financial support of a patron who understood the value of systematic astronomical work. On the 13th of August in the year 1847, just 1 month after Henke had found Hebe, Hind detected a faint point of light that did not correspond to any star recorded on his charts, and subsequent observations over the following nights confirmed that this object was indeed moving along a path consistent with an orbit in the region between Mars and Jupiter. This new asteroid received the name Iris, after the Greek goddess who served as messenger to the Olympian deities and who personified the rainbow that connected heaven and earth. The naming conventions for these minor planets had by this time settled into a pattern of drawing upon classical mythology, and each new discovery prompted discussions among astronomers about which divine figure might lend their name to the newly found world. Iris was a relatively bright asteroid as these objects go, and it could be followed with moderate-sized telescopes as it pursued its approximately 3-year orbit around the Sun, its path carrying it through the familiar constellations that marked the zodiacal band. Hind's success with Iris was followed quite promptly by another discovery, this one occurring on the 18th of October of that same year, when he identified yet another moving object that proved to be a previously unknown asteroid. This 8th minor planet was given the name Flora, honoring the Roman goddess of flowers and spring, whose festivals in ancient times had celebrated the renewal of life and the blossoming of vegetation. The discovery of 2 asteroids within the span of just over 2 months by a single observer working from one location suggested that these objects were perhaps more numerous than the long gap between 1807 and 1845 had implied. and that systematic searching with good equipment and reliable charts might yield additional finds with some regularity. The astronomical community began to appreciate that the apparent scarcity of asteroids had been an artifact of insufficient searching rather than an indication of their actual rarity in the solar system. The year 1848 brought another significant discovery, this one notable not only for adding a ninth asteroid to the catalogue, but also for extending the geography of asteroid discovery to a new location. On the 25th of April of that year, Andrew Graham, an Irish astronomer working at Markry Castle Observatory in County Sligo, identified a faint moving object that was subsequently confirmed as a new minor planet. Graham was employed at the private observatory established by Edward Joshua Cooper, a wealthy Irish landowner with a deep interest in astronomical research, and the Markry facility housed an impressive 13.5-inch refracting telescope that was among the largest in the world at that time. The asteroid Graham discovered was named Metis, after the Titan goddess of wisdom and deep thought in Greek mythology, who according to ancient stories was the first wife of Zeus and the mother of Athena. This discovery held particular significance as the first asteroid found from anywhere in the British Isles, demonstrating that the search for these elusive bodies had truly become an international endeavour involving observers across multiple nations and institutions. The contribution of Italian astronomers to this expanding field of research proved especially noteworthy during these years, with the work of Annibale de Gasparis at the Capodimonte Observatory in Naples deserving particular mention for its productivity and careful methodology. De Gasparis worked under conditions that modern observers might consider quite modest, employing a 6-inch Mers refractor that, while an excellent instrument of its type, was considerably smaller than the telescopes available to some of his contemporaries in wealthier observatories. The Mers firm of Munich had established itself as one of the premier manufacturers of refracting telescopes during this period, and their instruments were renowned for the quality of their optical glass and the precision of their mechanical mountings. De Gasparis made the most of his equipment, combining technical skill with extraordinary patience and a thorough knowledge of the star fields through which asteroids were likely to pass. On the 12th of April in 1849, De Gasparis detected an object that would be confirmed as the 10th asteroid, receiving the name Hygeia after the Greek goddess of health and cleanliness, from whose name we derive our modern word hygiene. Hygeia proved to be a particularly interesting discovery from a physical standpoint, as subsequent observations revealed it to be one of the larger asteroids, with a diameter exceeded among the known minor planets only by Ceres, Pallas, and Vesta. Despite its considerable size, Hygeia had escaped detection during earlier searches because its surface reflects sunlight rather poorly, giving it a relatively dim appearance when viewed from Earth. The discovery of such a large object so late in the sequence of finds suggested that the asteroid belt might contain numerous bodies of substantial size that remained hidden simply because they were dark or because they had not yet passed through regions of the sky being actively monitored by astronomers. De Gasparis continued his productive work at Naples, and on the 11th of May in 1850 he added another asteroid to the catalogue, bringing the total to 11. This new object received the name Parthenope, a choice that reflected both classical mythology and local Italian heritage, as Parthenope was one of the sirens of Greek legend and was also associated with the founding mythology of Naples itself, the ancient Greek colony having been established near the supposed tomb of this mythological figure. The naming of Parthenope thus honored both the astronomical tradition of drawing upon classical sources and the proud history of the city where the discovery had been made, a gentle acknowledgement of the local context within which scientific work always takes place. John Russell Hind had not been idle during this period of expanding discoveries, and he contributed another asteroid to the growing list when, On the 13th of September in 1850, he identified his third minor planet from the Regent's Park Observatory. This 12th asteroid was named Victoria, and while the name evokes the Roman goddess of victory, it was also understood as a tribute to the reigning British monarch, Queen Victoria, who had ascended to the throne in 1837 and whose long reign was associated with a period of considerable scientific and industrial progress in Britain. The dual significance of the name was typical of the era, when astronomical nomenclature could serve both classical and contemporary commemorative purposes without contradiction. By the close of 1850, astronomers could count 12 known asteroids, and when a 13th was discovered early in 1851, the previous understanding of the solar system as containing 4 major and 4 minor planets had been thoroughly superseded by a recognition that the region between Mars and Jupiter was populated by numerous small bodies whose total count remained unknown. The rapid multiplication of discoveries during this brief period of less than 5 years had fundamentally changed the questions astronomers asked about these objects, shifting attention from whether additional asteroids existed to how many there might ultimately prove to be and what their presence revealed about the formation and evolution of the solar system. The role of improved star charts in enabling this acceleration of discoveries cannot be overstated, for the successful identification of a moving asteroid depends entirely upon having accurate reference points against which motion can be detected. The Berlin Academy had undertaken an ambitious program of star charting during the earlier decades of the century, dividing the celestial sphere into 24 one-hour sections and systematically recording the positions of stars down to quite faint magnitudes. These charts proved invaluable for asteroid hunting because they allowed observers to quickly identify any point of light that did not correspond to a catalogued star, flagging potential asteroids for follow-up observation. The completion of Hora XXI of these charts in 1845, just as the new era of asteroid discovery was beginning, provided observers with excellent coverage of important regions of the sky through which asteroids frequently passed. The practical methodology of asteroid detection during this period involved the careful comparison of the observed sky against these reference charts, a process that required both patience and excellent visual acuity. An astronomer would typically spend long hours at the eyepiece, methodically checking each star in a given field against its expected position, and any discrepancy might indicate either a charting error, an observational mistake, or, most excitingly, a previously unknown moving object. The discovery of a potential asteroid would then need to be confirmed through repeated observations over subsequent nights, with the apparent motion of the object carefully measured to ensure it was consistent with an orbit in the asteroid belt rather than representing some other phenomenon such as a distant comet or an error in observation. The emerging international competition among asteroid hunters added a certain energy to the field, as observatories in Germany, England, Ireland, Italy, and other nations vied to add new discoveries to their respective tallies. While this competitive atmosphere remained largely collegial, with astronomers freely sharing observations and calculations to help confirm each other's discoveries, there was undeniable prestige attached to being the first to spot a new member of the solar system. The priority disputes that occasionally arose regarding who had first observed a particular asteroid reflected the genuine importance attached to these discoveries, even as the growing frequency of finds began to make each individual discovery seem somewhat less momentous than those of the pioneering era. Perhaps most significantly, the period between 1847 and 1850 established that asteroids were a numerous class of objects rather than rare curiosities, and this realization prompted deeper thinking about what their presence implied for theories of solar system formation. The old hypothesis of Olbers, that the asteroids represented fragments of a destroyed planet that had once orbited between Mars and Jupiter, remained popular, but the proliferation of discoveries raised new questions about the mechanics of such a catastrophe and the expected distribution of debris. Other astronomers began to consider alternative explanations, including the possibility that the asteroids represented material that had never coalesced into a single planet, perhaps due to the gravitational influence of massive Jupiter disrupting the accretion process. These theoretical debates would continue for many decades, informed by each new discovery and each improved measurement of asteroid orbits and physical properties. The 12 asteroids known by the end of 1850, soon to become 13 and then many more, represented a fundamental shift in astronomical understanding, transforming the solar system from a relatively simple arrangement of widely spaced worlds into a more complex structure containing countless smaller bodies whose movements followed intricate gravitational patterns. The observers who contributed to this expansion of knowledge, working through long nights at their telescopes in London, Naples, Sligo, and Berlin, had opened a new chapter in planetary science, though they could scarcely have imagined how many additional chapters would follow as the search for minor planets continued into subsequent decades and eventually into our own time. And so we come now to the instruments themselves, to the telescopes and the clocks and the careful methods by which these early observers went about their patient work of searching the night sky. For it is one thing to speak of discoveries, and quite another to understand the quiet labor that made such discoveries possible. The hours spent in cold observatories adjusting brass screws by candlelight, the painstaking recording of numbers in leather-bound ledgers, the slow accumulation of data that would eventually reveal those faint wandering points of light we call asteroids. The technology of this era was not flashy or dramatic, but rather a testament to careful craftsmanship and methodical observation. And there is something deeply restful in considering how these astronomers worked with such limited means and yet achieved so much. Giuseppe Piazzi, who discovered Ceres on the first night of the 19th century, conducted his observations from the Palermo Observatory in Sicily using an instrument of remarkable precision for its time, a 5-foot vertical circle constructed by the English instrument maker Jessie Ramsden. This device, which had cost the considerable sum of £1,114, was not a telescope in the way we might imagine one today, but rather a precisely graduated circle mounted vertically, through which an observer could measure the altitude of celestial objects with extraordinary accuracy. Ramsden was among the finest instrument makers of his generation, and his work for Piazzi represented the culmination of decades spent perfecting the art of dividing circular scales into their precise angular measurements. The vertical circle allowed Piazzi to determine the positions of stars and other objects with an accuracy that exceeded most contemporary instruments, and it was this precision that enabled him to notice the slight movement of what he initially took to be a new star, but which proved to be something far more interesting. The instrument stood in a room with walls thick enough to moderate the temperature fluctuations that could distort metal scales, and Piazzi would have observed through it on clear Sicilian nights, recording his measurements by the light of carefully shielded candles whose flames were kept steady and whose positions were arranged so as not to interfere with his dark-adapted vision. In the German town of Lilienthal, not far from Bremen, Johann Hieronymus Schroeder had assembled what was arguably the most impressive private observatory in Europe during the closing decades of the 18th century and the opening years of the 19th. Schroeder, who served as the chief magistrate of Lilienthal, devoted his considerable personal fortune to the construction of ever larger reflecting telescopes, instruments whose primary mirrors gathered the faint light of distant objects and brought them to focus for study. His greatest instrument was a reflecting telescope of 27 feet in focal length, an enormous device requiring a complex mounting structure and considerable effort to operate, yet capable of revealing details on the surfaces of planets and of detecting objects too faint for smaller instruments. The reflecting telescopes of this period used mirrors made of specular metal, an alloy of copper and tin that could be polished to a high reflectivity but which tarnished readily in the damp air and required frequent repolishing to maintain its optical quality. Schroeder's observatory became a gathering place for astronomers interested in the systematic study of the heavens, and it was there that the informal group known as the Celestial Police held their meetings, coordinating their search for the planet they believed must exist in the gap between Mars and Jupiter. Tragically, during the upheavals of the Napoleonic Wars, French troops occupied Lilienthal in 1813 and Schroeder's observatory was destroyed. His great 27-foot telescope and all his other instruments lost to the conflict. The scientific records he had accumulated over decades were scattered or burned, and the aging astronomer, who had invested so much of his life and resources in the study of the heavens, never recovered from the loss. He died just 3 years later, and the Lilienthal Observatory passed into memory, a reminder of how fragile the pursuit of knowledge can be in times of war. The period following the destruction of Lilienthal coincided with a gradual but significant shift in the technology of astronomical observation, a transition from the reflecting telescope, with its speculum metal mirrors, to the refracting telescope, with its glass lenses. This change was made possible largely through the work of Joseph von Fraunhofer, a Bavarian craftsman and optical scientist who transformed the art of lensmaking into something approaching a precise science. Fraunhofer worked at the Munich Optical Works, an institution that under his guidance became the foremost producer of high-quality astronomical lenses in the world, and his innovations addressed the fundamental problem that had long plagued refracting telescopes: the tendency of simple glass lenses to break white light into its component colors and thus produce images surrounded by distracting colored fringes. This phenomenon, known as chromatic aberration, had led many astronomers of the 18th century to favor reflecting telescopes, whose mirrors focus all colors of light equally. Fraunhofer developed methods for producing achromatic lenses, compound lenses made of two different types of glass whose properties were carefully matched to cancel out the color separation and bring all wavelengths of light to a common focus. His lenses were ground and polished with unprecedented care, their curves calculated mathematically and executed with tolerances that surpassed anything previously achieved, and the telescopes fitted with Fraunhofer objectives quickly proved their superiority for the precise positional work required in asteroid hunting. The instrument that perhaps best exemplified this new era of refractor dominance was the Great Dorpat Refractor, installed in 1824 at the Dorpat Observatory in what is now Tartu, Estonia. This telescope, with its objective lens measuring 9 6/10 inches in diameter, represented a new standard in astronomical instrumentation, and its mounting, designed by Fraunhofer himself, introduced the equatorial configuration that would become standard for serious astronomical work. In an equatorial mount, one axis of the telescope's rotation is aligned parallel to the Earth's axis, so that the slow drift of stars across the sky caused by our planet's rotation can be compensated by turning the telescope around a single axis at a steady rate. This arrangement greatly simplified the task of tracking celestial objects during extended observations, and the Dorpat refractor, under the direction of Friedrich Wilhelm Struve, demonstrated what such an instrument could achieve in skilled hands. The crisp, steady images produced by Fraunhofer's achromatic lenses allowed observers to measure stellar positions with new precision and to detect faint objects that would have been lost in the optical imperfections of earlier instruments. Though Struve himself focused primarily on the measurement of double stars, the capabilities demonstrated by the Dorpat refractor influenced the design of instruments at observatories across Europe, and subsequent asteroid discoveries benefited from the improved optics that followed from Fraunhofer's work. The detection of an asteroid required more than simply seeing a faint point of light in the telescope's field of view, for the sky is filled with thousands upon thousands of stars, and an asteroid, at first glance, appears no different from any of them. What distinguishes an asteroid is its motion, the slow drift against the background of fixed stars that reveals it to be a member of our solar system rather than a distant sun. The observers of this period developed methods for detecting this motion that, while laborious, proved effective, and these methods can be considered the precursors to the blink comparator technique that would later revolutionize such searches. The basic approach involved careful visual comparison of star charts drawn on successive nights, a process requiring both artistic skill and meticulous attention to detail. An observer would select a region of sky and, over the course of several hours, sketch the positions of all visible stars within that region, noting their relative brightnesses and their distances from one another with as much accuracy as eye and hand could achieve. On the following night, and the night after that, the same region would be observed again, and new charts prepared showing the positions of stars as they appeared on those occasions. By comparing these charts, laid side by side or overlaid upon a light table, the observer could search for any point of light that had shifted its position relative to its neighbors. A star that had moved, even by a small amount, was immediately suspect, deserving of further observation to determine whether its motion continued and what trajectory it might be following. This process was slow and demanded great patience, for a single evening's observation might yield nothing of interest, and weeks or months of work could pass without the reward of a new discovery. Yet it was through precisely such patient comparison that most of the early asteroids were found. Accurate timekeeping was essential to this work, for the position of a celestial object could only be meaningfully recorded if the moment of observation was precisely known. The Earth rotates continuously, and the apparent positions of stars change from moment to moment as the sky wheels overhead, so that an observation made at one instant differs from an observation made a few minutes later. To reduce these observations to a common reference frame, to compare them with predicted positions or with observations made on other nights, required knowing the time to within a fraction of a second. The observatories of this period relied upon clocks of the highest quality, often adapted from the marine chronometers developed for determining longitude at sea. These instruments, with their temperature-compensated balance wheels and their carefully jeweled bearings, could maintain a steady rate for weeks at a time, drifting by only a few seconds per day and thus providing a reliable time base against which observations could be referenced. Each observatory maintained its clocks with careful attention, comparing them regularly against astronomical phenomena of known timing, such as the transits of stars across the meridian, and recording their rates of gain or loss so that corrections could be applied to the observed times. The soft ticking of these precision timepieces formed a constant background to the work of observation, a gentle pulse underlying the astronomer's nightly labors. For the precise determination of star positions, the instrument of choice was the meridian circle or transit circle, a telescope mounted so as to swing only in the north-south plane and thus to observe objects precisely as they crossed the local meridian, the imaginary line running from the north point of the horizon through the zenith to the south point. By noting the exact moment when a star crossed the meridian, as indicated by its passage across fine wires or threads stretched across the telescope's field of view, and by reading the altitude of the telescope from its graduated circle at that instant, an observer could determine the star's coordinates with considerable accuracy. The Berlin Academy Star Map Project, which played such a crucial role in the discovery of Neptune and which assisted in the search for asteroids, was based upon observations made with such instruments. This ambitious undertaking divided the sky into 24 sections, each corresponding to 1 hour of right ascension, and assigned each section to a different astronomer who would prepare a detailed chart showing all stars down to a certain limiting brightness. The resulting horror sections, as they were called, provided a reference against which new observations could be compared, making it far easier to detect any object that did not belong, any wandering body that had strayed into the field since the chart was prepared. The chart that Carl Ludwig Henke used when he discovered Asteroid in 1845, and again when he found Hebe 2 years later, was one of these Berlin Academy maps, and its completeness allowed him to recognize immediately that the point of light he was observing was not recorded among the fixed stars. The conditions under which these observations were made were far removed from the climate-controlled, electrically illuminated observatories of later generations. The dome rooms of early 19th century observatories were lit by candles or oil lamps, their flames carefully shielded to preserve the observer's night vision and to prevent stray light from entering the telescope. The astronomer worked in near darkness, with only enough illumination to read the graduated scales of the instruments and to record observations in the logbook. This recording was done by hand, with pen and ink, the observer pausing between measurements to write down the numbers that would later be transcribed and analyzed. The calculations required to reduce raw observations to useful coordinates were performed manually as well, using tables of logarithms and trigonometric functions, a process that might take many hours for a single night's work. The observatories themselves were often cold in winter. Foreheating would create air currents within the dome that would disturb the steadiness of the telescope's images, and observers wrapped themselves in heavy coats and gloves, pausing periodically to warm their hands before returning to the eyepiece. There is something quietly admirable in this picture of the early asteroid hunters at their work. These patient men in their cold observatories, recording their numbers by candlelight, comparing their hand-drawn charts night after night in search of a tiny point of light that might prove to be something new. Their technology was simple by modern standards, yet they used it with skill and dedication, and their discoveries opened a new chapter in our understanding of the solar system. The instruments they employed, from Piazzi's vertical circle to the great Dorpat refractor, from the precision clocks ticking softly in their cases to the carefully printed horror charts of the Berlin Academy, formed a system of interlocking capabilities that made possible what no single device could achieve alone. The discoveries made between 1801 and 1850 did far more than add a handful of small objects to the catalogues of known worlds. They transformed, in ways both subtle and profound, how astronomers understood the very structure and history of our solar system, and they established methods of observation and calculation that would serve the science of celestial mechanics for generations to come. What began as a search for a single missing planet became something altogether different, something richer and more complex, and in the process, the tidy mathematical expectations of the previous century gave way to a more nuanced picture of the space between Mars and Jupiter. This is the story of that transformation, told slowly, as befits an evening when the mind is ready to wander gently through ideas rather than race toward conclusions. When the search for a planet between Mars and Jupiter began in earnest at the close of the 18th century, astronomers were guided by a simple and elegant expectation. The Titius-Bode law, that curious numerical progression that seemed to predict the distances of planets from the Sun with remarkable accuracy, suggested that something ought to exist at approximately 2.8 astronomical units from our star. The discovery of Uranus in 1781 had seemed to confirm this pattern, and so the gap between Mars and Jupiter became not merely a puzzle but something closer to an embarrassment, a blank space where nature had apparently failed to follow her own rules. When Giuseppe Piazzi found Ceres on the first night of the new century, the astronomical community responded with satisfaction, as though a missing piece of a jigsaw had finally been located and fitted into its proper place. The solar system, it seemed, was complete. But then came Pallas, in 1802, and suddenly the picture grew complicated. Here was another object, moving in a similar region of space, yet following an orbit far more inclined and eccentric than any respectable planet should possess. And then Juno in 1804, and Vesta in 1807, and with each new discovery the notion of a single missing planet became harder to sustain. What had seemed like the filling of a gap became instead the opening of a question, and astronomers were forced to confront the possibility that the Titius-Bode law, for all its pleasing mathematical regularity, did not describe a deep truth about planetary formation but rather a coincidence, or at best an approximation that nature felt no obligation to honor in every particular. The death of the missing planet theory came not in a single moment of refutation but through a gradual accumulation of awkward facts. Each new asteroid made it clearer that this region of the solar system was populated not by one substantial world but by many small ones, scattered across a broad zone of space like pebbles strewn along a beach. By the time the Great Drought of Discovery ended in 1845, and new asteroids began appearing with increasing frequency, the idea of a single missing planet had been quietly abandoned by most serious astronomers, replaced by the recognition that what existed between Mars and Jupiter was something more like a debris field, a population of minor bodies whose total mass was far less than anyone had initially supposed. This recognition brought with it a new question, one that occupied considerable attention in the early decades of asteroid science. If these small bodies were not themselves a planet, might they perhaps be the remains of one, the fragments of a world that had once existed whole but had since been destroyed? This hypothesis, most closely associated with Heinrich Wilhelm Olbers, the discoverer of Pallas and Vesta, proposed that a single planet had once occupied this region of space but had been shattered by some catastrophic event, perhaps a collision with a comet, perhaps an internal explosion, leaving behind the asteroids as its scattered remnants. It was an appealing idea, dramatic in its implications and tidy in its explanatory power, and it dominated much of the theoretical discussion during the early years of asteroid science. Yet even in its heyday, the exploded planet hypothesis faced serious objections, and these grew more compelling as observations accumulated. The most damaging criticism concerned the total mass of the asteroid belt, which even by the 1830s was understood to be remarkably small. If all the known asteroids were gathered together into a single body, that body would be far smaller than any of the major planets, smaller even than our own moon by a considerable margin. Where, then, had the rest of the original planet gone? No satisfactory answer emerged, and as decades passed and more asteroids were discovered, the problem only grew worse. The combined mass remained stubbornly insufficient to account for a proper planet, and the exploded planet hypothesis, while never entirely forgotten, gradually lost its place as the preferred explanation. The true significance of what lay between Mars and Jupiter would not become fully clear until later in the century, when the American astronomer Daniel Kirkwood published his observations concerning certain gaps in the distribution of asteroid orbits. Kirkwood, working with the accumulated orbital data from decades of careful observation, noticed that asteroids were not spread evenly throughout the belt but were conspicuously absent from certain orbital periods, specifically those periods that stood in simple ratios to the orbital period of Jupiter. An asteroid completing 3 orbits for every 1 orbit of Jupiter or 2 orbits for every one, would experience repeated gravitational tugs at the same points in its orbit, and over millions of years these accumulated perturbations would gradually shift the object into a different orbit altogether. The Kirkwood gaps, as they came to be known, revealed the invisible hand of Jupiter shaping the structure of the asteroid belt, and they demonstrated that this region of space was not a static collection of debris but a dynamic environment, constantly being sculpted by gravitational forces. Though Kirkwood published his findings in 1866, well after the period we have been considering, his work depended entirely upon the precise orbital calculations that had been made during the early decades of asteroid discovery. Without the painstaking measurements of Ceres and Pallas and Juno and Vesta, without the dozens of asteroids found in the 1840s and early 1850s, without the careful determination of orbital elements by generations of mathematicians, the gaps would have remained invisible. The scientific legacy of the early asteroid hunters extended far beyond their own lifetimes, providing the raw material for insights they themselves could never have anticipated. Even the language used to describe these objects became a matter of scientific debate, and the terminological discussions of this period reflect the uncertainty that astronomers felt about where exactly these new discoveries fit within the existing categories of celestial objects. William Herschel, the great observer who had discovered Uranus, proposed the term asteroid, from the Greek word for star-like, because when viewed through a telescope these objects appeared as mere points of light rather than as disks like the major planets. Others preferred the term planetoid, emphasizing the planet-like nature of their orbits, and still others favored minor planet, a designation that acknowledged their membership in the planetary family while clearly marking their subordinate status. These debates were not merely semantic but touched upon real questions about the nature and origin of these bodies, and the fact that all 3 terms remained in use well into the 20th century suggests that no single word ever fully captured what asteroids were. Quite apart from these theoretical questions, the practical work of tracking asteroids drove important advances in the methods of astronomical calculation. The techniques pioneered by Carl Friedrich Gauss for determining the orbit of Ceres became the foundation for all subsequent work in this area, and his approach to the problem, which involved deriving an orbital solution from the minimum necessary observations and then refining that solution as additional data became available, remained the standard methodology for more than a century. Gauss demonstrated that it was possible to calculate a preliminary orbit from just 3 observations, provided those observations were sufficiently precise and well-spaced in time. And this insight transformed the practical work of astronomers confronted with newly discovered objects that might fade from view before an extensive series of measurements could be made. Johann Franz Encke, who worked closely with Gauss and later became director of the Berlin Observatory, refined these methods further and applied them to a wide range of problems in celestial mechanics. His calculations of the orbit of the comet that now bears his name demonstrated the power of these techniques, and his work on asteroid orbits helped establish the standard format for reporting orbital elements that would be used throughout the century and beyond. The 6 orbital elements, specifying the size and shape of an orbit, its orientation in space, and the position of the body along that orbit at a given moment, became the universal language for describing the motion of any object in the solar system, and the computational methods for predicting future positions from these elements became increasingly refined and reliable. The work of tracking asteroids also demanded, and therefore fostered, international cooperation of a kind that had not previously existed in astronomy. The observations needed to maintain accurate orbits required coordination across national boundaries, and the journals that facilitated this coordination became essential infrastructure for the science as a whole. Franz Xaver von Sachs Monatlich Korrespondenz, founded in 1800, served as an early forum for the exchange of astronomical information, and when that publication ceased in 1813, its role was eventually taken up by the Astronomische Nachrichten, founded in Hamburg in 1821 by Heinrich Christian Schumacher. This journal, published in German but circulating throughout Europe and beyond, became the principal venue for announcing new discoveries and reporting observational data, and its pages record the gradual accumulation of knowledge about the asteroid belt through the 1830s and 1840s. Through these journals, astronomers in different countries could share their observations within weeks or months of making them, allowing for the kind of collaborative work that accurate orbit determination required. An astronomer in London might observe an asteroid on one night, an astronomer in Paris on another, and an astronomer in Berlin on a third. And from these combined observations, a mathematician in any of those cities could calculate an improved orbit. This pattern of international cooperation, informal but effective, established precedents that would shape the organization of astronomy for generations to come, and it was driven in large part by the practical demands of asteroid work, which could not be accomplished by any single observatory working alone. Beyond these specific contributions, the early decades of asteroid science served as a training ground for precision positional astronomy of all kinds. The skills required to discover and track these faint objects, the careful attention to coordinate systems and time measurements, the disciplined approach to error analysis and uncertainty quantification, all of these became essential competencies for working astronomers, and many who began their careers searching for asteroids went on to apply these skills to other problems entirely. The generation of astronomers who came of age in the 1820s and 1830s learned their craft in part through the demanding work of asteroid observation, and they carried these methods with them into whatever areas of research they subsequently pursued. By 1850, 13 asteroids were known, a number that seems almost quaint from our present perspective. Today, our catalogues contain not thousands but millions of these small bodies, and spacecraft have visited several of them, revealing surfaces of rock and dust, sometimes gathered into rubble piles held together by their own feeble gravity, sometimes showing signs of ancient impacts or more recent thermal processing. We have learned that asteroids are not uniform but diverse, comprising different compositions and histories, some primitive remnants of the early solar system and others fragments of larger bodies that differentiated and then broke apart. We have recognized the asteroid belt not as a failed planet or the remains of a destroyed one, but as a population of planetesimals that never managed to coalesce, their growth stunted by the gravitational influence of nearby Jupiter before they could accumulate into anything larger. All of this later knowledge rests upon foundations laid in the first half of the 19th century, when patient observers with modest telescopes scanned the sky night after night, and brilliant mathematicians developed the tools needed to make sense of what they found. The transformation of our understanding of the solar system that began with Piazzi's observation on the 1st of January 1801 has continued ever since, but the essential recognition that the space between Mars and Jupiter contains not emptiness but abundance, not a single missing world but a multitude of small ones, was the achievement of those early years. That recognition came slowly, through the accumulation of observations and the gradual abandonment of expectations, and it stands as a reminder that scientific understanding rarely arrives in a single flash of insight, but more often emerges through the patient work of many hands over many years, each contribution building upon those that came before, until what once seemed strange becomes simply the way things are.